The James Webb Telescope is 1.5 million kilometers from Earth. That's 4 times farther than the Moon. This space telescope, the size of a tennis court, can see things that happened 13.5 billion years ago, almost at the beginning of everything that exists. Scientists expected important discoveries, but what James Webb is showing is changing everything we thought about the universe. It found enormous galaxies that shouldn't exist so early in time, water in impossible places, and even signs of life on distant planets. How can a machine that weighs only 6 tons see the birth of the first stars and maybe answer the biggest question of all? Are we alone in the universe? Subscribe to the channel, leave your like and comment from what part of the world you're watching. Get comfortable and relax. Let's begin. What kind of place lets a telescope float in space, stay cold, and hold a steady view for hours without shaking? The James Webb Space Telescope sits about 1.5 million kilometers from Earth, circling the Sun near a region called the second Lagrange point. A Lagrange point is a place in space where the pull of gravity from the Sun and Earth and the motion of a spacecraft can balance in a useful way. Near this second point, Webb follows a small looping path while it orbits the Sun. In this position, the Sun and the Earth are always on the same side of the observatory. That steady geometry lets a large shield block heat and stray light. It also means the mirror and instruments can live in deep cold for years. Cold is essential for infrared work because warm parts would glow and drown out the faint signals the telescope needs to measure. Webb left Earth on 25 December 2021. The launch placed it on a path toward its distant post. The trip took weeks. During the cruise, the observatory unfolded in steps. A key job was to deploy and tension a sun shield with 5 distinct layers. Another was to swing out and lock the parts that hold the primary mirror and the secondary mirror. Each action was commanded and checked carefully from the ground. The full unfolding and cool down took time because large structures in space must settle before they can hold a very stable shape. The sun shield is central to how Webb works. It has 5 thin layers that reflect and radiate heat away. Each layer is shaped and spaced so that heat leaks as little as possible from the sun side to the cold side. With the Sun, Earth, and Moon kept to the same side, the shield creates permanent night for the mirror and instruments. On the warm side, solar panels and antennas face the Sun. On the cold side, the telescope optics and science instruments sit in continuous shadow. This separation allows steady temperatures. Steady temperatures keep the telescope shape constant, which keeps images sharp. The primary mirror is 6.5 meters wide. It is made of 18 hexagonal segments. The segments are beryllium, a light metal that holds its shape when very cold. Each hexagon has a very thin layer of gold on its surface. Gold reflects infrared light well, which is the kind of light Webb studies. The hexagon pattern fills the mirror's circle efficiently. The gaps between segments are narrow and shaped to limit extra light patterns in the images. The mirror sits on a rigid support structure that must hold the correct shape as the whole system cools to cryogenic temperatures. Each mirror segment can move with tiny steps in several directions. Small actuators behind the segments do this work. After launch and cool down, engineers performed a process called wavefront sensing and control. In simple terms, the telescope looked at a bright star and recorded the pattern of light from each segment. Software measured how each piece was tilted or curved relative to the ideal shape. Commands then nudged the actuators. The cycle repeated many times. The goal was to bring all segments into a single common focus, so the 18 pieces act like one large mirror. This careful alignment can be touched up during the mission when needed, though the structure is stable and changes are small once the observatory reaches its operating temperatures. Those temperatures are low. Most optical parts and the near-infrared instruments operate near 40 Kelvin. Kelvin is a temperature scale that starts at absolute zero, where thermal motion is as low as physics allows. 40 Kelvin is far below the freezing point of water. At such cold temperatures, the telescope's own glow in infrared becomes very weak. One instrument, which studies mid-infrared light, runs even colder, near 7 Kelvin. It uses a dedicated cryocooler. The cooler uses stages that carry heat away step by step and radiate it into space on the warm side. Its design avoids vibrations that would blur images. This extra cold step is needed because mid-infrared light is more easily overwhelmed by warm surfaces. The overall structure uses lightweight materials that stay stiff when chilled. The support for the mirrors and instruments must hold tight tolerances. It cannot sag or twist as the observatory moves or as the sun angle changes within its allowed range. Designers chose materials and shapes that hardly change size with temperature. Joints, trusses, and panels were tested on the ground in thermal vacuum chambers. Tests measured how parts would behave once cooled. These tests informed the alignment plan and the safety margins used during unfolding and tensioning. On the warm side sits the spacecraft bus. It provides power, communications, thermal control for the warm electronics, and the systems that point and steady the line of sight. A solar array converts sunlight into electricity. Batteries smooth out changes during brief events when power draw shifts. Antennas send recorded science data to Earth and receive commands. The main computer schedules tasks, handles health checks, and coordinates the instruments. Pointing control rests on several tools. Reaction wheels spin inside the spacecraft to turn the observatory gently without firing thrusters. To know its angle, the observatory uses gyroscopes and star trackers. A gyroscope measures rotation. A star tracker takes pictures of the sky and matches star patterns to a catalogue, giving an exact orientation. For science observations, a fine guidance sensor locks onto a guide star near the target. It feeds tiny corrections to keep the aim steady while the science instrument takes a long exposure. This steady pointing is vital. Many of Webb's targets are so faint that hours of exposure are needed. If the pointing drifts, the signal smears and the data lose detail. The observatory can rotate within limits to point at many places in the sky. It cannot look close to the sun because that would flood the cold side with heat. It also has limits near the anti-sun direction to protect structures and maintain power and communications. Within the allowed region, the scheduling team plans observations to avoid sudden large changes in sun angle. Smooth changes help keep temperatures stable. Stable temperatures keep the optics and instruments in calibration. This careful planning also manages the momentum stored in the reaction wheels. At times, thrusters offload momentum to keep the wheels within safe speeds. These brief events are planned to avoid times when a long, unbroken exposure is needed. Stray light control is another part of the design. The telescope has baffles and black coatings that reduce off-axis light from bright sources. The shapes of the mirror edges and support structures are chosen to avoid scattering light into the instruments. The 5-layer shield reduces the thermal glow from the warm side, and the instrument housings further block unwanted light. All these steps aim to ensure that the only light that reaches the detectors comes from the target and from the sky background, not from the observatory itself. After unfolding, the observatory entered a commissioning phase. The instruments cooled to their operating temperatures. Detectors reached their target values for noise and gain. The team measured the focus across the field and tuned each mirror segment. They checked imaging and spectroscopy modes. They tested the moving parts inside instruments such as filter wheels and grating wheels. They checked the multi-shutter array in the near-infrared spectrograph, which can open and close tiny doors to select many sources at once. They calibrated the fine guidance loops and the handoffs between acquisitions and science exposures. During this period, the observatory also refined its small orbit around the second Lagrange point with brief thruster burns. These actions, called station keeping, keep the path stable and safe. Data handling follows a clear path. Science exposures are recorded on solid-state memory. At set times, the observatory points its antennas to relay data to Earth through deep space communication networks. The round-trip delay in radio signals is several seconds, so the observatory operates with a planned sequence and sends status reports regularly. On the ground, pipelines process raw data into calibrated products. They correct for detector effects, apply wavelength and position solutions, and remove artifacts. Calibration files reflect the actual temperature and alignment at the time of each exposure, so the data are consistent. This flow from photons to science use depends on the observatory staying stable in temperature and pointing. The choice of beryllium for the primary mirror segments balances mass, stiffness, and behavior at low temperatures. Beryllium can be polished to a precise figure and tends to hold that figure when cooled, which reduces how much correction is needed in space. The gold coating is very thin. It is thick enough to reflect infrared wavelengths well, yet thin enough to keep weight low and to avoid stress as the mirror chills. Behind each segment sits a set of actuators for small tip, tilt, and piston motions, plus devices to adjust the curvature slightly. These allow the wavefront control process to co-phase the whole mirror to a level where the image quality matches design goals. The mid-infrared instrument's cryocooler is a complex unit with several stages. It moves heat along a path from cold heads near the instrument to radiators on the warm side. The cooler must avoid shaking the telescope. To do this, it balances moving parts and isolates them from the cold optical bench. The flow of heat must be steady because changes would move parts by tiny amounts and affect image quality. Engineers monitor the cooler and the temperature sensors closely. They adjust settings only when needed to keep everything calm. While the cold side is kept dark, the warm side must handle fluctuating sunlight as the observatory points to different parts of the sky. The power system and thermal blankets on the warm structures maintain a safe range. Communication antennas must maintain links to Earth. This drives some limits on how fast the observatory can slew from one target to another. The operations team sequences observations to meet science goals while keeping the system within its thermal and pointing budget. The location near the second Lagrange point brings other benefits. The Earth does not block the view often. This means that many targets are visible for long stretches. The absence of Earth's shadow on the warm side avoids cycles of heating and cooling. Fewer cycles mean less stress on materials over time. That helps the observatory stay in good health. Fuel is saved for station keeping and momentum management. The launch placed the observatory on a path that avoided the need for large burns after arrival. Careful use of thrusters during the mission extends life further. With these choices, the observatory keeps a margin of fuel for years, allowing a long program of observations. During science operations, the fine guidance sensor plays a quiet but central role. It watches a guide star and sends tiny corrections many times per second. It must work across a range of sky brightness and with different guide star colors. It must handle slight changes in focus as temperatures drift. The sensor shares its housing with an instrument that can take slitless spectra. This shared module reduces mass and complexity on the cold side. It also makes the guiding system more robust because it was built to high standards equal to the science instruments. Everything in the design supports the same goal: measure very faint infrared light with high precision. The distance from Earth reduces interference and keeps the Sun and Earth on one side. The 5-layer sun shield blocks heat and stray light. The large, cold mirror collects photons efficiently. The instruments are tuned for the wavelengths where dust, molecules, and early galaxies shine. The pointing system lets the observatory stare for long periods without blur. The cooling keeps detector noise low. The structure keeps its shape even as it swings to new targets within its allowed range. Working at such low temperatures introduces risks, so the mission includes many checks. Sensors watch temperatures at many points. Attitude measurements confirm that the pointing does not drift. Engineers review health data daily. When minor issues appear, they are addressed with small updates to software or observing plans. This cautious approach keeps the observatory in a safe zone. It also keeps science data consistent over time, which helps when observations from different months must be combined. From its place in space to the tips of its mirror segments, Webb is built around the needs of infrared astronomy. Cold optics, stable pointing, and a large collecting area make it possible to record light that has crossed vast distances or that is emitted by very cool material. The sun shield, the actuators, the star trackers, and the cryocooler are all parts of one system. Each piece reduces noise or error in a different way. Put together, they turn faint signals into clean measurements. This is the foundation that allows the observatory to open the infrared window with clarity, reach very faint targets, and hold long exposures that reveal details about stars, dust, planets, and the first galaxies. What does infrared light reveal that our eyes cannot see at all? With the telescope held cold and steady far from Earth, the next step is understanding the kind of light it measures. Infrared light is light with wavelengths longer than visible light. A wavelength is the distance between one crest of a wave and the next. The unit used here is the micrometer, which is 1/1,000,000th of a meter. Webb records infrared light from about 0.6 micrometers to about 28.5 micrometers. This wide reach includes faint glow from stars and gas, warmth from dust grains and ices, and very old light that the expansion of the universe has stretched to longer wavelengths. Infrared light is important for two simple reasons. Many cool objects in space give off most of their energy in this band, including dust and many common molecules. Also, light that left the first galaxies started out at shorter wavelengths and then shifted to longer wavelengths as space expanded. By the time that light reaches us, it often sits in the infrared. If we want a full story of stars, gas, dust, and the first structures, we need to use infrared. This is why Webb's cold state matters so much. Any warm surface gives off infrared energy. If the telescope or the instruments were warm, their own glow would swamp the faint signals from space. The 5-layer shield, the distance from Earth, and the careful thermal design bring the mirror and the near-infrared instruments to temperatures near 40 Kelvin. One mid-infrared instrument sits closer to 7 Kelvin with help from a dedicated cooler. At these temperatures, the observatory's own glow is very weak, and the detectors can listen for faint signals for long periods without being flooded by unwanted light. On the short side of Webb's range, the sensors are made from mercury-cadmium telluride. This material turns incoming infrared photons into electric charge with high efficiency when it is cold. On the long side of the range, the sensors are made from silicon arsenide. This material holds sensitivity at wavelengths where many other detectors fall quiet. Each material has its strengths. Together, they cover nearly the whole span that the mission needs, from the edge of red visible light out to mid-infrared wavelengths where cold dust and many molecules emit. Detectors are never perfect. they add a small amount of random variation called noise. They can also register a tiny current even when no light is present. Cooling reduces both effects. Signals are read carefully to limit extra noise from the readout process. The observatory is designed to keep temperatures constant because small temperature changes can shift detector behavior. Stability keeps the response known and repeatable. The mission's sensitivity rests on a simple chain. A large cold mirror gathers photons efficiently. The optics deliver the light cleanly to the detectors. The detectors convert photons to electrons with low extra noise. The pointing stays steady for a long time. Background light from the telescope and the sky stays low and constant. Calibrations remove small detector quirks. When these pieces are in place, the observatory can collect light for many hours and build up a clean signal from very faint targets. Astronomers describe faintness with a scale called AB magnitude. On this scale, larger numbers mean fainter sources. Deep images from Webb reach AB magnitude 30 in imaging. Sources that faint are invisible to the human eye and were not accessible in earlier surveys. Reaching this level requires long integrations, careful scheduling for dark sky backgrounds, and processing that preserves tiny signals while removing artifacts. The sky itself has a faint infrared glow. Some of it comes from very small dust grains in the solar system that are warmed by sunlight. Some of it comes from distant, unresolved sources. Operations teams plan observations to avoid brighter background regions when depth is needed. The telescope's shield also blocks light from the sun and earth, which keeps the local background low. With this control, the noise from the sky and telescope can be limited so that the dominant uncertainty comes from the faint target itself. Infrared light carries many clues about what it passed through or where it came from. Atoms and molecules absorb and emit at specific wavelengths. These sets of wavelengths are called spectral lines or bands. In the near-infrared, hot hydrogen and helium can produce strong lines from star-forming regions. In the mid-infrared, many common molecules such as water, carbon dioxide, methane, and carbon monoxide show clear features. Solids such as silicate dust and various ices have broad features as well. Measuring where these features appear and how strong they are tells us what is present and at what temperature and pressure. It also tells us how fast a source is moving away because motion shifts the position of lines toward longer wavelengths. To isolate these signals, Webb uses filters and dispersers. A filter is an element that allows only a chosen range of wavelengths to reach the detector. Imaging with different filters builds a color picture in the infrared. Those colors are not just for appearance. They measure how the brightness changes with wavelength. From that pattern, one can estimate distances to very remote galaxies and pick out objects with certain types of gas or dust. A disperser is a prism or a grating that spreads light out into a spectrum. Spectra reveal fine detail that imaging cannot, including line shapes and weak features that sit between the broader bands of light. The observatory supports imaging and spectroscopy at several levels of detail. Wide filters cover broad ranges of wavelengths for deep surveys. Narrow filters target specific features in gas and dust. Low-resolution dispersers spread light gently, which is useful for very faint sources. Medium and higher-resolution modes spread light further, which is useful to separate nearby lines and to measure motions through tiny shifts in wavelength. The stability of the telescope and the quality of the optics ensure that light stays in the correct place on the detector during long exposures, so lines do not blur and structures remain crisp. Field of view and pixel scale set what the observatory can map. Each pixel covers a tiny angle on the sky. The pixel size in the near-infrared is tuned to the sharpness delivered by the 6.5-meter mirror at those wavelengths. The field of view of each instrument defines how large an area can be captured in one exposure. For larger regions, the team moves the pointing in small steps to build mosaics, for better sampling and to reduce the impact of small detector defects. The team offsets the telescope by sub-pixel amounts between exposures. This practice increases image quality after the data are combined. Long observations must also deal with charged particles that strike the detectors. These are high-energy particles that cross the solar system. When one hits a pixel, it leaves a mark that can look like a bright spot or a streak. To handle this, detectors are read multiple times during a single exposure. This allows software to find and remove sudden jumps that are not due to light from the target. This method keeps the clean signal and throws away the false events from particles. Calibrations turn raw counts into physical measurements. Dark frames measure the detector response with no light. Flat fields measure how each pixel responds to uniform light. Wavelength solutions map position on the detector to wavelength for spectra. Distortion solutions map position on the detector to position on the sky for images. These steps correct small variations across the detector and small effects in the optics. The calibration files depend on temperature and instrument state, so the system tracks conditions and uses the best matching files for each exposure. The result is data that different teams can use in a consistent way. The wavelength range of Webb was chosen with purpose. Near the short end, around 0.6 micrometers to a few micrometers, the light from young stars and from the outer parts of early galaxies is strong. The ultraviolet light from those stars has been shifted into this band by cosmic expansion. The break in the spectrum caused by hydrogen absorption moves into these wavelengths at high distances, which helps select ancient galaxies. Around a few micrometers to the mid-infrared, warm dust and many molecules emit. This is where protoplanetary disks show their building blocks. This is where exoplanet atmospheres show water vapor, carbon dioxide, methane, and other gases. At the long end, near 20 to 30 micrometers, very cold dust and ices glow, and some special molecular lines appear that trace chemical processing in cold regions. Because the same hardware can image and take spectra across this full range, the observatory can study very different targets with a common frame. A deep image in the near-infrared can find candidates for very distant galaxies. Spectra across the near and mid-infrared can then measure exact distances and show which elements are present in those galaxies. In a star-forming region, images can reveal jets from young stars and cavities carved by radiation. Spectra can measure temperatures, densities, and shock traces across gas clouds. Around planets, time series in the near and mid-infrared can capture starlight filtering through a thin rim of atmosphere during a transit, and can record the thermal glow of a planet when it is visible alone. The sensitivity of the detectors, the cold environment, and the low background also support careful measurements of colors. Even small changes in brightness between two filters can carry meaning. For very distant galaxies, such changes can signal the sharp drop created by hydrogen absorption at a rest frame ultraviolet wavelength shifted by expansion. For disks and planets, small bumps and dips in a spectrum can reveal the presence of specific molecules. The key is that the measurement repeats when taken again. Stability over time and agreement across instruments where they overlap build confidence. Noise behavior sets the limit for faint signals. There is noise related to the random arrival of photons from the target and from the sky. There is noise from the detector electronics. There is noise from temperature drift. The mission design aims to keep the last two low and to make them well understood, so the first kind dominates. When photon noise dominates, longer exposure time improves the measurement in a predictable way. This is why steady pointing and thermal control are so important. If the background varies or the detector response changes during an exposure, the simple scaling with time no longer holds. The observation modes are chosen with these limits in mind. When the goal is very faint imaging, filters and pointing are selected to keep backgrounds minimal and to let long exposures run without interruption. When the goal is to measure a bright planet transiting a star, shorter exposures and faster readouts prevent saturation, and the guiding system keeps the star on the same pixels to avoid small errors from pixel to pixel differences. When the goal is mid-infrared spectra of cold dust, the cryocooler holds the instrument near 7 Kelvin, so that the instrument itself adds almost no glow to the signal. Data from Webb span a wide range of scales. A single exposure can capture a nearby star with a planet, or a piece of a distant galaxy cluster, or a patch of a nebula with shock fronts and filaments. A program can combine many exposures to map a large region or to watch a target as it changes with time. Each dataset comes with its context: the exact filter or disperser used, the exposure time, the orientation, the temperature of the instrument, the background level. This context lets teams compare measurements from different nights and different instruments, and it allows corrections when small drifts are found. The infrared window also gives access to light that has traveled a long time. The first stellar populations emitted radiation that was once in the ultraviolet. Cosmic expansion stretched that light into the near-infrared. Webb's sensitivity out to several micrometers is tuned to catch it. This is why deep surveys use near-infrared filters to find dropouts, which are sources that fade sharply in some filters and appear in redder filters. The pattern marks the presence of high redshift galaxies. Spectra then confirm the exact shift and show whether the galaxies host hot stars, gas outflows, or active nuclei. The same surveys often include mid-infrared imaging to test for dust and to refine estimates of the total energy output. Closer to home in cosmic terms, the mid-infrared holds the fingerprints of many simple molecules and of solid grains. Warm water vapor emits in bands across a few micrometers. Carbon dioxide has a strong feature near 4 3/10 micrometers and another at about 15 micrometers. Methane has several bands across this range. Silicate dust has a broad feature near 10 micrometers. Ices show features in absorption when they sit in front of a bright background and in emission when warmed gently. By measuring these features, Webb builds an inventory of materials in clouds and disks and tracks how they change with radiation and time. The instruments use well-defined sets of filters and dispersers to cover this territory. Each mode has been characterized on the ground and refined in space. Throughput, which is the fraction of incoming light that reaches the detector, is measured. Sensitivity, which is the faintest level of light needed for a given signal quality in a given time, is measured. Line spread functions, which describe how a sharp line is recorded in a spectrum, are measured. Point spread functions, which describe how a star looks in an image, are measured. These functions vary with wavelength. The operations and data pipelines record all the needed parameters so users can model and remove the effects and reach the underlying physical signals. Webb's design also anticipates the need to cross-check results. The near-infrared and mid-infrared sensors overlap in some wavelengths. Observers can measure a feature near the overlap with two instruments. Agreement increases confidence. If a difference is found, it can flag a calibration update. The fine guidance sensor keeps pointing steady during these tests so that differences are not due to drift. The cooler maintains a steady operating point. The thermal state of the observatory is monitored so that small changes can be included in the calibrations. All of this rests on simple ideas expressed with careful engineering. Keep the telescope and instruments cold and stable. Use detector materials that are well matched to the wavelengths of interest. Control stray light. Read the detectors in ways that reduce noise and flag unwanted events. Use filters to define colors and dispersers to reveal spectra. Calibrate, observe, and repeat. The payoff is a clear view into parts of the universe that remain hidden in visible light and a precise measure of gases and solids that set the stage for planets and life. From this base in the infrared window, the observatory's tools take shape. A camera optimized for the near-infrared builds the deep color images used to find distant galaxies and faint companions. A spectrograph in the same band splits the light of many sources at once so that distances and compositions can be measured. A mid-infrared instrument opens the cooler domain of dust, ices, and molecules, and can even mask starlight to reveal nearby planets. An additional imager and spectrograph provide flexible modes and the fine guidance needed for all of this to work. Together, they use the infrared reach and sensitivity described here to turn faint light into detailed knowledge across a wide range of targets. What tools inside Webb turn faint infrared light into clear information? The observatory carries 4 main instruments that work together across the infrared band. Each one has its own role, yet they share a common aim. They take the steady, cold light collected by the large mirror and record it as images and spectra that people can analyze. The design is simple in concept. One tool makes deep pictures to find and measure sources. Another splits light into its colors to read out composition and distance. A third opens the cooler mid-infrared where dust, ices, and many molecules emit. A fourth adds flexible modes that are useful for surveys and for tracking planets, and shares a housing with the guidance sensor that keeps the aim steady. The overlap between tools is intentional so that teams can cross-check results and move from finding to confirming to detailed study. A camera optimized for the near-infrared builds the base layer for much of Webb's work. It is called the Near-Infrared Camera, or NIRCAM. It takes very sharp images using many filters. A filter passes only a chosen slice of wavelengths. By switching filters, NIRCAM measures how each source's brightness changes with wavelength. This color pattern is not just a picture. It is a way to sort objects and to estimate distances for the most remote ones. The camera is built with 2 optical paths that can record 2 wavelength ranges at the same time. This happens through a splitter inside NIRCAM that sends shorter wavelengths to one set of detectors and longer wavelengths to another set. This means that a single pointing can capture 2 colors at once with matched detail. The pixel scale and the optics were chosen to match the sharpness that the 6.5-meter mirror can deliver at near-infrared wavelengths. This match keeps stars tight and small in the images, which helps detect faint sources near brighter ones. NIRCAM supports deep fields and focused targets. In deep fields, the camera stares for many hours through several filters. The pointing shifts by small amounts between exposures. These offsets reduce the impact of tiny detector defects and fill the gaps between detectors. Later, software combines the frames into a mosaic with clean sampling. In focused programs, the camera can frame a galaxy cluster, a nearby star with a planet, or a patch of a star-forming cloud. It can use narrow filters to isolate light from specific gases or wider filters to measure overall colors. The instrument also supports special masks that reduce starlight, which helps in some cases when looking for faint companions near bright stars. The camera's filter set was chosen to sample key features of galaxies and of molecules across the near-infrared. This strategy allows it to find promising targets for spectroscopy. Once candidates are found, the near-infrared spectrograph or NIRSPEC, reads their light in detail. A spectrograph spreads light by wavelength so that features can be seen and measured. NIRSPEC can do this in several ways. It has a grid of tiny doors called a micro-shutter array. There are about 250,000 shutters. Each shutter can open or close on command. By opening many small windows at once along rows, the instrument can record spectra for many sources in the same field. This multi-object ability makes efficient use of time in rich fields. NIRSPEC also has fixed slits that isolate a single source at a time with very clean background, and an integral field unit that takes a small patch of sky and records a spectrum at every point within that patch. This last mode produces a data cube with 2 spatial dimensions and 1 wavelength dimension. It is useful for mapping gas motions and for separating overlapping sources that are close together. NIRSPEC offers several levels of spectral detail. Low-resolution modes are used when sources are faint, and the aim is to measure broad features and overall slopes. Medium and higher resolution modes are used when the goal is to separate nearby lines, to measure gas motions from small wavelength shifts, or to detect weak features next to stronger ones. The instrument has wheels that hold gratings and prisms, and mechanisms that move them into the light path. Each position has a known response that is checked with calibrations. During an observation, the telescope may nod between positions so that background light from the sky and from the instrument can be measured and subtracted. The multi-object mode requires planning. Teams prepare a mask configuration that matches known source positions. The software avoids shutters that do not open cleanly and makes sure each spectrum will land on a clear spot on the detector without crossing another spectrum. When the field is very crowded, choices must be made about which targets to include. Even with limits, many tens to hundreds of spectra can be recorded in a single exposure. The mid-infrared instrument, or MIRI, opens the longer wavelengths from about 5 micrometers to about 28 micrometers. It operates in a colder state than the rest, close to 7 Kelvin, with help from a dedicated cooler. This extra step keeps the instrument's own glow very low. MIRI provides imaging and spectroscopy. Its imaging mode covers several filters chosen to capture key features of dust and molecules, such as the broad silicate bands and lines from simple gases. Its spectroscopic modes include a low-resolution slit for faint, broad features and a medium-resolution integral field unit that records a spectrum at every point across a small field. This allows the mapping of temperature, composition, and motion in warm dust and in gas close to star formation. MIRI also carries coronagraphs that block a star's core light so that structures and faint companions close to that star can be recorded. A coronagraph is a device that masks starlight while letting the surrounding region pass. It requires very stable pointing and careful calibration because small leaks of starlight can mimic a faint object if not controlled. MIRI's detectors respond to different sources of noise than the near-infrared sensors. The background from the telescope and the sky is stronger in the mid-infrared, so observations are planned to keep backgrounds as low and stable as possible. The instrument reads the detectors with patterns that separate real signals from drifts. Calibration includes measurements of the response to uniform light, of the exact wavelength map for each pixel, and of the way a sharp spectral line is recorded. These steps allow teams to recover faint features such as weak emission from water vapor or carbon dioxide in a disk, or thin lines from ions in a distant galaxy. Because MIRI works where many molecules and solids emit, it links chemistry to structure. It shows where ices survive, where grains grow, and where radiation heats dust. The Near-Infrared Imager and Slitless Spectrograph, or NIRISS, provides modes that add flexibility. Slitless spectroscopy takes a spectrum of every source in the field without using a slit. This is useful for surveys because many objects can be recorded at once without the need to pre-select targets. It is also useful when a slit might cut off part of a source, such as a diffuse cloud or a source that moves slightly. NIRISS includes a specialized mode for bright stars observed during planet transits. In this mode, the light is spread in a way that avoids saturating the detector and keeps the signal stable across time. Care is taken to model any small changes from the star itself because star spots and bright regions can alter the recorded spectrum. NIRISS shares a module with the Fine Guidance Sensor. The guidance sensor locks onto a guide star and sends small corrections many times per second, so the telescope holds a steady aim during long exposures. This steady aim supports all instruments. Without it, spectra would blur and images would smear. Each instrument carries moving parts such as filter wheels, grating wheels, shutter arrays, and masks. These mechanisms were designed and tested to operate at cryogenic temperatures. On orbit, engineers watch their performance closely. A filter that does not reach its index position can shift a band slightly. A shutter that sticks can reduce the number of targets in a pattern. The planning software takes known quirks into account. Observations include small offsets to avoid placing important data on known bad pixels. The processing pipelines flag and correct known patterns that come from readout electronics or from the detector material. Many of these steps are invisible to the astronomer who studies the final image or spectrum, but they are essential to keep the data reliable. The way these tools are used follows a practical flow. Deep imaging with NIRCAM finds sources and assigns basic colors. From those colors, teams make a list of candidates at different distances and with different properties. NIRSpec then measures spectra to confirm exact distances and to read out emission and absorption lines. These lines tell us about star formation rates, gas content, chemical elements, and motions. MIRI adds information about dust and cooler gas, filling in the mid-infrared part of the spectrum where many molecules are brightest. NIRISS can provide slitless surveys that sample many sources at once, or time series spectra during planetary transits. The result is a set of measurements across wavelengths that describe each target more completely than any single instrument could do alone. Even with this reach, there are limits that users respect. Very bright sources can saturate detectors if not handled with short exposures or special readout modes. Very faint mid-infrared targets can be limited by the background light that fills the instrument. Overlapping spectra in slitless modes must be untangled with careful modeling. In crowded fields, the micro-shutter array may not be able to open shutters for every source of interest without causing spectra to overlap. Programs weigh these trade-offs and choose modes that fit their goals. Often, a survey will use a mix of strategies. Wide, shallow imaging can find rare, bright objects. Narrow, deep imaging can reach the faintest ones. Multi-object spectroscopy can capture large samples efficiently. Integral field spectroscopy can dissect a few key sources in great detail. The instruments were built by teams across several countries. They were calibrated on the ground and then refined in space. The response of each filter, grating, and detector is measured. The sensitivity to point sources and to diffuse emission is measured. The sharpness of images and the spread of spectral lines are measured. These measurements are not one-time events. They are repeated to track slow changes over years. The archive stores the calibration files along with the data so that future reprocessing can improve past products. This habit matters when new lab measurements refine the wavelengths of molecular lines, or when new methods reduce detector noise a little more. The goal is consistency and transparency, so results from different teams can be compared fairly. The connection between instruments also appears in the scheduling. Some programs require the near-infrared and mid-infrared observations to be close in time so that any variable sources are measured in a consistent state. Some programs can separate the visits across months without losing meaning. The operations team balances these needs while keeping the observatory in a stable thermal state. For example, a sequence may start with NIRCAM imaging to establish a target list, followed by NIRSPEC multi-object spectroscopy for redshifts and basic line measurements, and then MIRI spectroscopy to probe dust and molecules. NIRISS may add slitless spectra for fainter sources that were not included in the multi-object masks. The fine guidance sensor supports each step by keeping the pointing stable. A clear example of the synergy is the way distant galaxy programs work. NIRCam imaging identifies sources with sharp drops in brightness between selected filters, a sign that hydrogen absorption has moved into the near-infrared due to cosmic expansion. NIRSPEC spectroscopy then confirms the exact wavelength of the break and of key lines, which gives a precise distance. MIRI checks for warm dust and for mid-infrared lines that trace the conditions inside those galaxies. NIRISS can add broader slitless spectra that fill in gaps for sources not included in the multi-object masks. Through this chain, researchers move from a list of candidates to a set of confirmed objects with measured properties. In the nearby universe, the flow is similar, but the details change. In star-forming regions, NIRCAM maps structures and jets. NIRSPEC measures gas motions and line ratios that reveal temperatures and densities. MIRI traces warm dust and identifies ices and simple organics. NIRIS provides rapid spectra across fields where a slit would miss diffuse arcs and shocks. For planets, NIRISS and NIRSPEC record time series during transits in the near-infrared, while MIRI records thermal emission at longer wavelengths. Together, they constrain the mix of gases and the presence of clouds or hazes. In direct imaging cases, MIRI's coronagraphs and NIRCam's high-contrast modes reduce starlight to reveal faint companions. Each mode comes with its own calibration strategy, and the overlap in wavelength between instruments helps catch subtle errors. The reliability of the whole suite relies on the same foundations described earlier. Cold, stable temperatures keep detector noise low and optical shape steady. The fine guidance sensor holds the pointing. Reaction wheels and star trackers manage gentle motions. Thruster firings that would disturb long exposures are scheduled away from sensitive observations. The observatory systems record their state so that any small drift can be included in the processing. When these conditions are met, the instruments deliver data that can be combined across time and across modes without confusion. The path from a photon entering the telescope to a measured line in a spectrum is long, but it is built from simple pieces that repeat. The mirror focuses the light. An instrument selects a wavelength range and a mode. The detector records charge as photons arrive. The readout captures that charge as numbers many times during the exposure. Calibrations correct for known patterns. The final product is an image or a spectrum that reflects the sky with noise that can be measured. Confidence comes from checks. Features that appear in more than one filter or more than one instrument are more secure. Patterns that repeat in separate visits are more likely to be real. Differences that persist may point to variability in the source or to a calibration that needs an update. This mix of openness and caution is part of the culture around Webb's data. With these tools, the observatory can move from seeing to understanding. A faint blotch in a deep image becomes a galaxy with a measured distance and with lines that speak to its stars and gas. A warm patch in a nebula becomes a map of molecules and grains. A tiny dip in a star's brightness becomes a list of gases in a planet's atmosphere. The suite was built to support this full journey. It covers a continuous band in wavelength. It offers both imaging and spectroscopy. It balances wide views with detailed probes. It works with a guidance system that keeps everything still and sharp. This is how faint light from the earliest times and from the cool material that builds planets is turned into data that describe what the universe is made of and how it changes. How far back in time can this telescope truly see? With the mirror aligned and the instruments ready, astronomers pointed Webb to small regions of sky and let it collect light for very long stretches. The aim was simple: find the faintest galaxies and measure how far away they are. In the language of cosmology, distance is expressed through redshift. Redshift tells how much the universe has stretched the wavelength of light during its journey to us. Light that started out at shorter wavelengths arrives at longer wavelengths. Larger redshift values point to earlier times. Webb's near-infrared camera is built to catch that stretched light, and its filters are chosen to spot the sharp drop caused by hydrogen absorption that moves through the infrared as distance increases. Deep programs use this property in a practical way. The camera takes images through many filters. Astronomers then look for objects that vanish in the bluer filters and appear in the redder ones. That drop is the sign of the hydrogen break moving into the near-infrared. It is a first clue that the source sits at a very high redshift. These candidates are faint. Many are close to the detection limit of the images. To make sure they are real, the observations repeat through small offsets, and the data are combined with methods that remove detector artifacts and cosmic ray hits. The result is a clean mosaic with a catalogue of sources and their colors measured as precisely as possible. One of the largest efforts of this kind is known as JWST. It uses very deep imaging and spectroscopy in well-studied fields. The imaging comes from the near-infrared camera, which reaches to AB magnitude 30 in several filters when many hours of exposure are added together. The spectroscopy comes from the near-infrared spectrograph, which spreads the light of selected sources to reveal features at known wavelengths. In this program, two compact objects stood out. They showed the expected sharp drop in the right place and very blue colors at redder wavelengths. Spectra then confirmed redshifts above 13. They are labeled JWST 13-0 and JWST 14-0. These names mark their field, their survey, and their rank in distance among confirmed objects. The properties of these sources are striking in a measured way. Their images are tiny even for Webb's sharp view. Size estimates place them below about 500 parsecs across. A parsec is a unit of distance used in astronomy. The blue colors in the ultraviolet part of their spectra suggest very little dust and very young stars. When model spectra that describe young stellar populations are fit to the data, the rate of star formation can reach tens of solar masses per year in some cases. These numbers depend on the assumed mix of stars and on how much light is lost to dust, so they come with uncertainties. Still, they show that even small systems at early times can turn gas into stars at a fast pace. Deep images also reveal many fainter sources with similar color patterns. These lie just above the detection limit and require careful measurements. Teams test how complete their selections are by inserting fake sources into the data and checking how often they are recovered. This step matters because the faintest bins can be undercounted if many sources fall below the detection threshold. The tests also help set errors on the number counts and on the color measurements. With these controls, a picture forms. The early universe hosts many small blue compact galaxies and a few that are surprisingly bright for their time. Another major effort is called CEERS. It covers a wider area at somewhat shallower depth, and it uses a mix of imaging and spectroscopy to build a large sample of distant galaxies. The near-infrared camera finds candidates through the same color drop method. The spectrograph then targets many of them together using its micro-shutter array. This grid of tiny doors opens on the chosen sources and closes elsewhere so that hundreds of spectra can be recorded in one shot. The spectra reveal the sharp hydrogen break when it falls in the covered band. They also show emission lines from elements such as oxygen, hydrogen, and neon. These lines carry information about the temperature and density of gas and about the rate of star formation. The patterns also confirm the redshift with high precision. From these programs and others like them, one theme emerges. There are more bright galaxies at redshifts between 10 and 12 than some earlier models predicted. This point will be refined and balanced as more spectra come in, but the trend holds. It suggests that gas was gathered and turned into stars efficiently in some halos during the first few 100 million years. Why this happened is an open question. It could be that the earliest gas cooled and collapsed faster than expected. It could be that the first rounds of feedback from young stars were weaker at very low metallicity. It could be that we are still missing some bias in how we count or select sources. The data are a guide rather than a final answer. The precision of the redshifts is central to the story. Color-based selections are powerful, but they can be fooled. Certain kinds of lower redshift galaxies can have strong emission lines that fall into the filters and make them look like high redshift dropouts. Dusty sources can also mimic some colors under specific conditions. Spectroscopy breaks these degeneracies. It shows the true position of the hydrogen break and the locations of key lines. In some cases, follow-up spectra have shifted candidates to lower redshifts and changed their inferred properties. This is not a failure. It is how the method is meant to work. Imaging casts a wide net. Spectra tell which fish are really there. The sizes of the earliest galaxies carry clues about how they formed. A compact size below a few hundred parsecs suggests that stars are packed into small regions. At such times, gas inflows can be directed into the central parts by the overall potential of the halo or by the geometry of the cosmic web. The presence of strong oxygen lines in the spectra points to hot, young stars and to gas that has already been enriched slightly by the deaths of very massive stars. The mix of lines indicates low metal content overall at levels well below that of the Sun. This matches the blue colors, which also point to little dust. In a few cases, very faint mid-infrared detections have hinted at dust, but these are rare at the highest redshifts. Where dust is present, it may be produced quickly by supernovae or by fast winds from massive stars. The star formation rates derived from ultraviolet light assume that the light escapes the galaxy without heavy absorption. If dust is present, the true rates would be higher than the raw ultraviolet estimate. For most of the highest redshift cases, the very blue colors and the non-detections at longer wavelengths suggest that dust corrections are small. Still, teams check for energy balance by seeking faint far-infrared emission with other observatories. When dust is detected, it sets an early time for solid particle formation and challenges models of grain growth, which may need to proceed faster than previously thought. Another measurable quantity is the shape of the ultraviolet continuum. This slope responds to the age of the stellar population and to the amount of dust. Very steep blue slopes point to very young stars and to little dust reddening. The earliest galaxies often show such slopes. This is consistent with recent bursts of star formation. It is also consistent with top-heavy stellar populations, where more massive stars are present in a larger fraction than in the local universe. Direct proof of the exact mix of stellar masses is hard to obtain, but the line ratios and continuum slopes together can limit the options. The deep programs also test the method of finding distances from colors. These photometric redshifts are built by fitting model spectra to the measured points across many filters. The fits return a best estimate and an uncertainty. For most cases, the estimates match the spectroscopic redshifts well. For some cases, a lower redshift solution can fit nearly as well if certain emission lines fall into particular filters. These are the cases where spectra are most needed. The community has learned to flag sources where the color pattern can be fit by two different distances and to target those for spectra early. This practice improves the purity of high redshift samples. When looking at the whole set of deep images, it is clear that the earliest galaxies are not uniform. A few are bright and compact. Many are faint and barely resolved. Some appear in small groups. Some show hints of structure, with clumps that could be regions of intense star formation. The spectroscopic data add to this by indicating a range of ionization states and gas densities. This diversity points to different assembly histories even at very early times. Some halos may have had steady inflow and quiet growth. Others may have had mergers or strong inflows that triggered bursts. These patterns are starting to be mapped by integral field spectroscopy, which can show how gas moves within each galaxy. In some, ordered rotation is present. In others, the motions are turbulent. These details will grow in number as more programs add this mode to their deep fields. In addition to the hydrogen break, one line often used to confirm distances is Lyman alpha, which is a line from hydrogen at a specific ultraviolet wavelength. At very high redshift, this line is often weak or absent because the gas between galaxies is partly neutral and absorbs it. When it is present, it can mark a region where the gas is already ionized. When it is absent, it can mark a region where neutral gas still dominates. The pattern of detections and non-detections across fields gives hints about the patchy nature of ionization. This is a clue that connects early galaxies to the larger state of the universe at that time. The reach of the deep programs depends not only on depth but also on area. Small fields that go very deep find many faint sources and a few bright ones. Wider fields that go slightly less deep find more bright sources and improve statistics at the top end. This balance matters because the number of bright galaxies at early times has a strong effect on models of structure growth. Early reports from wide fields showed more bright candidates than expected. Some of these were later moved to lower redshifts by spectroscopy, reducing the tension. Even after these changes, a real excess seems to remain. The level of the excess is under active study. A clear case that shows why spectra are vital is an object once thought to sit at an extremely high redshift in a wide field. It had colors that matched a very distant galaxy. After spectroscopy, it turned out to be much closer. Its strong emission lines at lower redshift had boosted the brightness in certain filters, creating a false high redshift signature. This example has improved selection methods. It has led to updated template libraries that include strong line emitters at lower redshifts, and to the use of priors that reduce the chance of such misclassifications. It has also encouraged teams to invest time in spectroscopic confirmation before making strong claims about extreme distances or masses. The time dimension adds another layer. Deep fields are sometimes revisited. This improves the depth and checks for variability. For galaxies at these distances, real changes in brightness over a year are not expected, but faint transients in the field can be present and can confuse selection if not identified. Consistent fluxes across visits add confidence that the detected sources are steady galaxies rather than temporary events. In parallel, different instruments can observe the same field. Near-infrared measurements from Webb, optical data from earlier missions, and radio or sub-millimeter data from ground-based arrays together build a richer view. The absence or presence of emission at long wavelengths can support or challenge the idea that dust is present in a given source. Taken together, the first deep programs sketch a new map of the early universe. Galaxies appear earlier and in larger numbers than many models had forecast. They are small and blue, with signs of intense star formation and little dust. Some host active nuclei. Some sit in regions where hydrogen is already ionized. Their spectra show oxygen, carbon, and neon at low levels, meaning that chemical enrichment started quickly. These facts guide updates to how we think gas collapsed into halos, how stars formed at very low metal content, and how radiation from early stars and black holes affected their surroundings. At the same time, caution runs through the interpretation. Photometric selections can be fooled by special cases. Line strengths can change the apparent colors in ways that mimic greater distance. Sizes near the resolution limit are uncertain and need careful modeling of the image blur. Star formation rates depend on assumptions that may not hold at the earliest times. Teams address these points by seeking spectra, by using multiple instruments where they overlap, by combining fields to reduce the impact of cosmic variance, and by testing their methods with simulations and with fake source recovery. This work sets the stage for a more precise question: how many of the bright candidates truly sit at the claimed distances, and how massive are they when distances are fixed by spectra rather than by colors alone? The answer depends on careful measurements of line positions, on the separation of young stellar light from emission lines, and on modeling that allows for different amounts of dust and different star formation histories. It also depends on recognizing when a lower redshift object with strong lines is masquerading as a higher redshift one. The shift from images to spectra and the corrections that follow bring the counts and the masses onto firmer ground. Why can a single precise measurement change the whole picture of a distant galaxy? In the deepest images, the first step is to find candidates. The second step is to measure exact distances with spectra. That second step changes more than distance alone. It changes how we see brightness, it changes how we calculate mass, and it changes what we think about how fast stars were being born. The near-infrared camera gives colors that suggest a distance. The near-infrared spectrograph then fixes that distance by finding the true position of the hydrogen break and by detecting lines from elements in the gas. With that anchor, the mid-infrared instrument and the other near-infrared modes add detail about dust, molecules, and the older stars that set the bulk of the mass. A color-based distance estimate is called a photometric redshift. It comes from fitting model spectra to the points measured through many filters. The method works well when the pattern is clear and when the sources are not too faint. But there are traps. Strong emission lines can fall into the filters and boost the light in ways that mimic a different distance. Dust can dim and redden light in ways that also mimic a different distance. When both effects line up in an unusual way, a nearer galaxy can look like a much more distant one. This is why spectra are so important. A spectrum shows the exact wavelengths where features sit. It shows several lines at once. It shows the real shape of the break. These details remove the room for confusion. The corrections that follow from spectra are concrete. Imagine a source where colors imply a very large distance. The photometric fit assigns a redshift and then maps each filter to a rest wavelength. Mass is then fit by comparing the overall energy output to models of stellar populations. If the true redshift is lower, every part of that mapping shifts. The filters now probe different parts of the spectrum. The rest wavelengths change. Features that were thought to be from old stars can turn out to be bright emission lines from gas. Since emission lines can add a lot of light in a narrow part of a filter, the total light used to estimate mass may drop when that contribution is removed. When this happens, the inferred mass drops too. A well-known case illustrates the point. In a wide field, a source called CEERS-93316 had colors that placed it at an extremely high redshift. Its brightness at that implied distance suggested a very large mass. Follow-up spectroscopy found instead a much lower redshift. The colors had been boosted by strong oxygen and hydrogen lines at that lower distance. Once the true distance and line strengths were known, the mass estimate fell by a large factor. This was not a rare fluke. It was a lesson about the need to include strong lines in model libraries and about the need to confirm extremes with spectra. When the distance is fixed, other quantities follow. The rate of star formation can be measured from the ultraviolet light corrected for dust, or from emission lines that track massive young stars. The size of the galaxy can be measured more accurately because the scale conversion from angle to distance is now known. The age of the stars can be constrained by the shape of the spectrum near the Balmer break, which is a feature in the optical part of the spectrum that appears when stars older than a few 100 million years contribute. At very high redshift, that feature moves into the mid-infrared, which is why Miri is valuable. If the mid-infrared flux is faint, the mass in older stars may be small. If the mid-infrared flux is stronger than expected from young stars alone, there may be a hidden older population that raises the mass. Early in the mission, some candidates seemed to have very large masses at very early times. Those claims relied on color-based distances and on fits that did not fully correct for emission lines. As spectra arrived, several redshifts moved to lower values. Once fixed, the mass-to-light ratios were revised. In addition, the strength of emission lines such as doubly ionized oxygen and hydrogen beta were measured directly. These lines can be extremely strong in young galaxies with low heavy element content. They can add a lot of flux to near-infrared filters. After subtracting them, the remaining continuum was lower, and so was the mass. The overall picture became more balanced. There does seem to be a real number of bright galaxies at redshifts around 10 to 12 that is higher than older models predicted. But the most extreme claims of mass dropped away when distances and lines were nailed down. Understanding how mass is inferred helps explain why these shifts are large. The total starlight we see is turned into a mass through models of stellar populations. These models depend on the mix of stellar ages, the chemical content of the stars, the amount of dust, and the assumed distribution of star masses when new stars form. In simple words, young stars put out a lot of light for each unit of mass. Old stars put out less light for each unit of mass. If you think a source is dominated by old stars, you assign a larger mass for the same light. If it is dominated by very young stars, you assign a smaller mass for the same light. Emission from gas lines is not starlight at all, so it should not be counted as part of the stellar mass. When lines boost the measured light and are not removed, the mass estimate is biased high. This is where the combination of instruments matters. NIRSPEC shows the line strengths directly. NIRCAM, with its wide filter set, measures the continuum shape across the near-infrared. MIRI extends that shape into the mid-infrared where old stars would contribute more. Together, they give a spectrum that is not continuous at every wavelength but that samples enough points to tell a clear story. When the data show a very blue continuum and extremely strong emission lines, the mass per unit light is low. When the data show a redder continuum and a clear break at the rest optical wavelengths, the mass per unit light is higher. Another source of correction comes from the way noise scatters measurements. At the faint end, there are many more sources just below the detection limit than just above it. Random noise can push some of the fainter ones upward so that they appear in the catalog. Fewer measured sources get pushed downward and lost. This asymmetry means the number of sources in the faint bins can be inflated by noise. A similar effect can happen near the bright end when the number of sources drops steeply with brightness. Noise can push a few more moderate sources into the bright bin than it pushes down. Teams simulate this behavior by inserting fake sources into the data and recovering them. They then correct the counts. When this is done, some of the early excess in bright counts reduces. It does not vanish, but it becomes less extreme. Gravitational lensing is another subtle factor. Mass along the line of sight can magnify a background source slightly. This effect can make a galaxy appear brighter and larger than it really is. In strong lensing fields near massive clusters, this is an intentional tool that helps see very faint objects. In blank fields, the average magnification from random alignments is small, but individual objects can still be affected. When spectra are taken, the foreground structures can be identified, and lens models can estimate the magnification. Applying those corrections reduces bias in the bright end counts and in the inferred sizes and masses. Dust adds more complexity. Even a little dust can make a galaxy look older and more massive if the modeling does not allow for low metallicity dust properties appropriate to early times. With spectra, teams can use line ratios to estimate the amount of dust that blocks light in the nebula regions. They can compare that to the continuum slope to see if the stars suffer the same amount of dimming. If dust is present, the corrected ultraviolet light implies a higher true star formation rate. If dust is absent, the very blue slopes are consistent with little dimming and with recent bursts of star formation. Both cases exist. The pattern across many galaxies shapes our view of how quickly dust formed after the first stars. The distribution of brightnesses, often called the luminosity function, is a compact way to summarize the population. It tells how many galaxies exist at each brightness in a given volume and at a given time. The bright end is sensitive to how fast the largest halos gather gas and turn it into stars. The faint end is sensitive to how common small halos are and to how star formation proceeds in shallow potential wells. Webb data suggest that the bright end at redshifts between 10 and 12 is higher than earlier expectations. The faint end appears steep, meaning there are many faint galaxies. Both results affect our view of ionization, because both bright and faint systems contribute photons that can ionize hydrogen. Mass functions, which count galaxies by stellar mass instead of by brightness, are harder to build at very high redshift. This is because the rest optical light that best traces old stars moves out of reach of the near-infrared filters and into the mid-infrared. MIRI can measure this, but not for every faint source in a deep field due to time limits and sensitivity. As a result, early mass functions carry larger uncertainties. Spectra help by fixing redshifts and by flagging cases where light is dominated by emission lines. With these controls, the high-mass tail becomes less populated than some first reports suggested. A few very massive candidates remain, and these set strong tests for models. But the number of such cases is modest when distances are secure and when lines are removed from the photometry. These corrections also affect the inferred ages of the earliest galaxies. When a strong rest optical break is present and the mid-infrared flux is high, models point to some older stars, which means star formation started earlier than the observed time. When the continuum is very blue and smooth with little mid-infrared flux, models point to a very young population dominated by massive stars. Spectra that show strong oxygen and hydrogen lines support the latter case. In several confirmed high redshift galaxies, the equivalent widths of these lines are very large, which is a signal of intense recent star formation with little contribution from older stars. That, in turn, lowers the mass estimate and raises the specific star formation rate, which is the rate per unit mass. The chain from imaging to spectroscopy also improves the maps of where early galaxies sit in space. With precise redshifts, clustering can be measured. If bright sources are more clustered than expected, it could mean that they live in rarer, more massive halos than models assumed. If they are less clustered, it could mean that temporary bursts make galaxies appear bright without a large underlying mass. These patterns are just beginning to emerge. They will influence how we connect early light to the growth of dark matter structures. Behind all of this lies the practical work of building better model libraries and better fitting tools. Teams have expanded their templates to include very strong emission lines at a range of metallicities. They have added nebular continuum, which is a smooth emission from ionized gas that can fill in parts of the spectrum. They have tested different star formation histories, including bursts and rising histories that may fit early times better than simple, steady models. They have updated dust laws to match low metallicity conditions. They have added priors, which are gentle constraints that reflect what is known from other data to reduce the chance that the fits wander into unlikely regions. These steps make photometric redshifts more reliable and make mass estimates more grounded when spectra are not yet available. The outcome is a clearer, though still evolving, view. There is a real population of bright galaxies at early times. Some are at very high redshift, confirmed by spectra. Their sizes are small, their colors are very blue, and their line strengths indicate young stars and low metal content. Their masses are significant but not extreme when lines are removed and when the true redshifts are set. A few candidate outliers remain and deserve more data. Spectra have corrected some early missteps, reduced the most dramatic claims, and strengthened the overall case that early star formation in some halos was efficient. These refinements have a purpose beyond bookkeeping. The number of bright and faint galaxies, their masses, and their star formation rates together set the budget of high-energy photons that can ionize hydrogen in the intergalactic medium. With secured distances and with corrected luminosities, we can count how much light is available to drive rionization. We can also look for the hydrogen-Lyman alpha line, which is a sensitive tracer of whether the space between galaxies is neutral or ionized. Spectra show when this line is present and when it is missing. Its presence or absence, along with the galaxy counts and masses, helps trace the timing and the uneven nature of the end of the cosmic dark ages. How do we know when space between galaxies changed from neutral gas to ionized gas? The story starts with hydrogen. After the early hot phase of the universe, protons and electrons combined to form neutral hydrogen. Much later, the first stars and black holes formed and emitted high-energy light. That light has enough energy to remove electrons from hydrogen. When this happens widely, the gas between galaxies changes state. This long change is called reionization. It did not happen everywhere at once. It started in small regions around sources and grew until those regions met. Webb's strength in the infrared allows a direct look at the galaxies that likely powered much of this change, and it records a key hydrogen signal that reacts to the state of the gas. That signal is called Lyman alpha. It is light from hydrogen at a specific ultraviolet wavelength. Neutral hydrogen scatters this light strongly. Ionized hydrogen does not. When the space around a galaxy is still mostly neutral, Lyman alpha usually does not travel far. When the space around a galaxy is ionized, the line has a better chance to reach us. Webb's near-infrared spectra shift this ultraviolet line into the band it can see. In some parts of the sky, and at some distances, the line is detected in galaxies. In other parts and at other distances, the line is absent even when other lines are present. This pattern already tells us that the gas was a mix of neutral and ionized regions during the period we are probing. The exact mix changes with distance and from place to place. Counting galaxies by brightness in the ultraviolet adds another piece. Webb's deep images measure how many galaxies exist at each ultraviolet luminosity at early times. The number rises steeply toward faint systems. This steep rise is often described as a steep faint end slope. It means that small galaxies are very common. Each small galaxy may form only a modest number of stars, yet the large total number of such galaxies can add up to a strong source of high-energy photons. These photons are the ones that ionize hydrogen. When we combine the counts of faint objects with their typical star formation rates, the result is a large photon budget. A budget alone is not enough. Ionizing photons must escape their galaxies. The fraction that escapes is called the escape fraction. It depends on how gas and dust are arranged. If gas and dust block many paths, fewer photons leave. If gas is full of holes, or if winds push channels open, more photons leave. Webb helps in two ways. First, it measures the color of the ultraviolet continuum. Very blue colors suggest little dust and young stars, which together point to abundant high-energy photons and fewer obstacles. Second, it measures emission line ratios. Strong oxygen lines and weak dust indicators suggest gas that is highly ionized and low in heavy elements. In such conditions, the escape fraction may be higher. These are indirect signs, but across many galaxies, they set a trend that favors escape in early, low-mass systems. The Lyman alpha line itself carries local clues. The profile of the line, when detected, is often shifted to wavelengths slightly longer than the rest position. This shift can result from gas outflows. When gas moves away from us, the line moves to longer wavelengths where it can slip through the surrounding neutral gas more easily. Webb's spectra can measure these shifts. They show that some early galaxies drive outflows. Outflows can open channels and increase the chance that ionizing photons leave. In other galaxies, the line is not detected even when other lines are strong. That absence is expected if neutral gas outside the galaxy remains abundant. Seeing both cases across similar distances points to a patchy state of the universe. To place these measurements on a timescale, we use another source of information. The cosmic microwave background carries a record of how many free electrons the average photon has scattered from since early times. That effect is called electron scattering optical depth. It does not give a detailed timeline by itself. It gives an integral over the whole history. When that integral is combined with Webb's counts of galaxies, with their inferred photon production, and with estimates of escape fractions, a picture emerges. It shows reionization starting early and finishing by redshift around 6. In words, by that distance, the space between galaxies is mostly ionized. This picture is not uniform. Fields studied with deep imaging and spectroscopy show variations. In some regions, the fraction of galaxies with detected Lyman alpha at a given redshift is higher. In other regions, it is lower. These variations can be explained by differences in the size and growth of ionized regions. Groups of galaxies can ionize a larger bubble more quickly. Isolated galaxies may sit in more neutral surroundings. Webb's fine sensitivity detects these patterns because it can record both the continuum light that sets the ultraviolet color and the faint lines that mark the local gas state. Metal lines provide further checks. Lines from oxygen, neon, and carbon appear in the near-infrared for high redshift galaxies. The strengths of these lines and their ratios respond to how hard the radiation field is and to how enriched the gas is with heavy elements. Early galaxies often show strong oxygen lines and low overall metal content, well below 1/10 of the Sun. Such spectra indicate hot, young stars that produce many ionizing photons. This reinforces the idea that many faint galaxies together can power reionization. Where dust is detected through very faint mid-infrared signals or longer wavelength observations, the ionizing output is still often large, but the escape fraction may be lower. The balance varies from galaxy to galaxy. The mapping of faint galaxies across the sky helps with another factor called clustering. If early galaxies are clustered, their ionized regions can overlap sooner. Webb's precise redshifts from spectroscopy reduce uncertainty in positions along the line of sight. With these distances in hand, teams can measure how strongly galaxies are grouped. Early results suggest that bright galaxies are indeed in dense regions. This would help carve larger ionized zones earlier. Fainter galaxies are more spread out but are numerous. Together, these patterns can generate a reionization process that grows in a patchwork with faster progress in dense regions. Another tool comes from radio wavelengths. Neutral hydrogen emits at a wavelength often called 21 centimeters. Arrays on the ground are trying to map this signal across large areas. They aim to see the contrast between neutral and ionized regions directly. These maps are still developing. When they become clearer, they will combine with Webb's galaxy maps. In regions where radio maps show more neutral gas, Webb should find fewer Lyman alpha detections. In regions where radio maps show less neutral gas, Webb should find more. Work along this line has begun with statistical measures, and it will grow as both kinds of data improve. Submillimeter measurements with facilities such as ALMA add detail about cold gas and dust in some of the same galaxies. Lines from singly ionized carbon and from oxygen at far infrared wavelengths trace gas that sits in and around star-forming regions. When such lines are detected in high redshift galaxies, they supply estimates of gas mass and of the scale of star-forming regions. When combined with Webb's ultraviolet and near-infrared data, they test whether dust could be hiding star formation that would otherwise increase the photon budget. In many early galaxies, the dust signal is weak or absent, which matches the very blue ultraviolet colors. In a few bright cases, dust is present even at early times. Those cases show that dust can form quickly and that not all early systems contribute equally to reionization. The efficiency of ionizing photon production is another key measure. It links the ultraviolet light we see to the number of ionizing photons produced. It depends on the age and metallicity of the stars and on the presence of binary stars that can keep stars hot for longer. Strong oxygen lines and very blue ultraviolet slopes imply high efficiency. Webb's spectra give direct access to both indicators. Across samples at high redshift, the values tend to be higher than in typical nearby galaxies. This difference supports faster ionization than would be expected if early galaxies had the same efficiency as later ones. Not all ionizing photons come from stars. Some come from active black holes. Webb has found signs of such activity in certain early galaxies through broad emission lines and through line ratios that point to very hot central sources. The number of these active nuclei at early times appears modest compared to galaxies without them. Their contribution to the global ionizing budget is likely smaller than that from stars in faint galaxies. However, near each active nucleus, the hard radiation can strongly affect the surrounding gas. It can carve out ionized regions and change the state of nearby hydrogen. This local effect matters when interpreting Lyman alpha detections and non-detections around those hosts. Because ionization is patchy, Lyman alpha is a noisy tracer when considered one object at a time. Its presence might mean either a local ionized region or a line shifted by outflows in a way that helps it escape. Its absence might mean neutral surroundings or a line profile that does not help escape. This is why teams look at statistics across many objects and across several fields. Fractions of detections at a given redshift, distributions of line strengths, and the relation of detections to galaxy brightness all help. Patterns that repeat across fields build confidence. Outliers are studied in more detail with deeper spectra. Integral field spectroscopy with near-infrared instruments adds motion maps inside some early galaxies. Where ordered rotation is present, it suggests a disk forming early. Where turbulence dominates, it suggests recent inflow or merging or strong energy input from stars. Gas motions influence line profiles, including Lyman alpha. An outflow moves gas and can allow more Lyman alpha to shift to wavelengths that pass. A static or infalling medium can trap the line more effectively. By linking gas kinematics to line detection, Webb connects internal physics of galaxies to the ease with which their light reaches us and affects their environment. Timing matters across the entire period. As we look to higher redshifts, the Lyman alpha detection fraction drops on average. At somewhat lower redshifts, closer to when ionization is mostly complete, the detection fraction rises. This trend matches the picture from the microwave background constraint and from galaxy counts. It gives a timeline that starts early and ends by redshift around 6 with uneven progress in between. The slope of this trend and its exact values in different fields help tune models of how fast ionized regions grow and how clustered the sources are. The growth of ionized regions changes the contrast of temperature and density in the gas between galaxies. This change feeds back on how new galaxies form, because gas that has been ionized and heated is harder to pull into the smallest halos. Webb's view of the faintest galaxies helps probe where this cutoff may lie. A steep, faint end slope suggests many small systems still manage to form stars. As ionization advances, the abundance of the very faintest galaxies may be reduced in ionized regions. Distinguishing this effect from observational limits is challenging. It will require larger samples and careful modeling. Uncertainties remain and are handled with care. Escape fractions are mostly indirect and use models. The conversion from ultraviolet light to ionizing photon production depends on stellar population assumptions that are still being refined. Lyman alpha transfer through gas involves complex radiative processes and geometry. Foreground contamination can affect both imaging and spectroscopy if not recognized. Teams try to reduce these uncertainties through cross-checks. They measure the same sources with different instruments. They repeat observations. They use simulations to test their selection and fitting methods. They keep track of biases that could raise or lower counts. Even with these cautions, the weight of the evidence points to a simple summary. Early galaxies are common and often very blue, with strong signs of hot young stars. Their number rises quickly toward low luminosities. Their light produces many ionizing photons, and a meaningful fraction of those photons likely escape. The gas between galaxies shows a mixed state with ionized bubbles that grow and merge over time. By redshift around 6, most of the volume is ionized. Variations across fields and within samples fit the picture of a patchy process driven by clustered galaxies, with added local effects from early active nuclei. This view sets limits on how fast energy sources must have grown. It also highlights places where radiation from compact central sources is already active. When broad lines mark hot gas near a central mass, that object is growing by drawing in matter. The same radiation that shapes its near surroundings also adds to the ionizing budget. The balance between star formation, outflows, and accretion onto central objects is therefore not only an internal story for each galaxy, it helps fix the state of space around them during these first few 100 million years. How can a black hole grow so fast, so early? A black hole is a region where gravity is so strong that not even light can escape. When gas falls toward a black hole, it heats up and glows. That glow carries clues about the black hole's mass and about how quickly it is growing. Webb's infrared spectra reach the rest ultraviolet and rest optical light from very distant galaxies. In that light, some galaxies show signs of central engines that are already active in the first few 100 million years. These signs include very broad emission lines from very fast gas close to a compact center and line ratios that require a harsh radiation field that stars alone cannot supply. One clear case comes from a field called CEERS. In a galaxy at redshift 8.7, Webb found broad emission lines and hot gas that together reveal a black hole of about 9 million solar masses. The phrase solar masses means the mass of our Sun used as a unit. The broadness of the lines comes from gas moving at very high speed near the black hole. The speed can reach a few thousand kilometers per second. The width of the line is the record of that speed. When combined with the brightness of the region, the width gives a mass estimate because faster gas close to a more massive center leaves a wider line. In this case, the result lands near 9 million solar masses at a time when the universe was still young. Another well-studied source, GN-Z11 at redshift around 11, shows strong metal lines in gas that appears to be under the influence of a central hard radiation source. Lines from elements such as nitrogen, carbon, and helium can be unusually strong and in patterns that are hard to make with stars alone. This does not by itself fix the black hole mass. It does point to activity in the nucleus. When such activity is present so early, it tells us that the seeds that made these black holes formed quickly and that the feeding of gas onto them must have been efficient. Feeding is not simple. There is a physical limit to how fast a black hole can gain mass when the infalling gas makes light. The light pushes outward on the gas. Gravity pulls inward. At some point, the push from light balances the pull from gravity. This balance sets an upper rate for steady growth called the Eddington limit. If a black hole grows close to this limit, it doubles its mass on a timescale of about a few tens of millions of years. A useful number is about 40 million years for a typical case. To go from a small seed to millions of solar masses in the first few 100 million years, the growth must stay near this limit for long spans, or the seed must start out large, or both. Seeds can form in at least two ways that are often discussed. One path is the death of very massive stars in the first generations. These can leave behind black holes with tens to hundreds of solar masses. Another path is the direct collapse of dense gas in special conditions that avoid breaking up into stars. That can make a seed with around 100,000 solar masses. The mass of the seed changes how strict the growth demands are. A small seed needs many doublings to reach millions of solar masses. A larger seed needs fewer doublings. Webb's detections of early active nuclei do not yet choose between these options on their own. They do set limits. If many early black holes are already near 10 million solar masses, either seeds formed early and heavy or steady feeding near the growth limit was common, or both. Spectra carry more than one clue. The shape of a broad line reflects both speed and the motions of gas around the black hole. If the gas is in a disk, some of the line shape looks different than if the gas is in a more random cloud. The exact line used depends on redshift. At very high redshift, rest ultraviolet lines are shifted into the near-infrared where Webb can see them. These include lines from carbon, nitrogen, and helium. At somewhat lower redshift, rest optical lines such as hydrogen beta and doubly ionized oxygen move into reach. The measured widths in these lines and the local brightness support the mass estimates. The narrower lines from gas farther out in the galaxy tell a different story. They trace the host's star formation and the conditions in the wider gas. Ratios between narrow lines help separate the contribution from stars and from the nucleus. In the CEERS case, a combination of broad and narrow lines shows both an active center and a compact star-forming host. The host galaxy is small and is forming stars quickly for its size. The coexistence of star formation and a growing black hole is a common theme in cosmic history. The two processes share the same gas supply. Outflows from young stars and from the nucleus can heat and move gas. These outflows can slow the feeding. They can also open channels through which radiation escapes. Webb's spectra show blue-shifted and red-shifted components in some lines. Blue-shifted parts point to gas moving toward us. Red-shifted parts point to gas moving away. Shifts of hundreds of kilometers per second are seen in several sources. These motions set the scale of energy input from both stars and the central engine. Growth rates are estimated by comparing the light from the nucleus to the mass estimate. If the nucleus shines near the Eddington limit, the feeding rate is at the physical ceiling for steady flow. If it shines well below that, the feeding rate is lower. For the early active nuclei found so far, many are at a large fraction of this limit. That is why they are visible at such distances. It also means that if this state lasts, the mass can rise quickly. Duty cycle is a term for the fraction of time a black hole spends in an active state. Long duty cycles near the growth limit are one way to reach millions of solar masses early. Shorter bursts would require more massive seeds or special events to catch up. The chemical state of the gas near these nuclei tells us something about their history. The presence of oxygen, carbon, and neon means that massive stars have lived and died nearby. That enrichment can happen fast, within a few tens of millions of years. The low overall level of metals, often below 1/10 of the Sun, matches the blue colors and the lack of heavy dust in many early hosts. This mix allows intense radiation to move through the gas. It also means that cooling and fragmentation in gas clouds may have been somewhat different than in later times, which could favor direct collapse in rare spots, though this remains under study. A natural question is whether X-rays are needed to confirm active nuclei. At these redshifts, X-ray detections are hard because the sources are faint and the distances are great. Webb does not measure X-rays. Instead, it relies on rest ultraviolet and rest optical indicators. Strong high ionization lines, broad components, and certain line ratios are the main signs. Where these appear together, the case for an active nucleus is strong. In some cases, the line ratios alone can be made by very hard stellar spectra at very low metal content. This is why broad lines are so important. Very fast gas in a compact region is a secure sign of a central massive object. Host galaxies give important context. Sizes are small, often below a few hundred parsecs. Star formation rates can be tens of solar masses per year. Gas densities inferred from line ratios are high. Ionization parameters, which describe the ratio of ionizing photon density to gas density, are high as well. These conditions support strong radiation fields that can affect the surroundings. In some fields, galaxies with active nuclei sit in regions where Lyman alpha is detected more often. This can be because their hard radiation helps ionize local gas. In other regions, Lyman alpha remains absent even near bright sources, which suggests that the larger scale gas is still neutral. Both cases fit a patchy reionization picture. The presence of early black holes also limits how models can assign gas to halos. If there is not enough gas inflow to the central regions, feeding will stall. If outflows are too strong for too long, the nucleus will starve. Simulations that include gas cooling, star formation, supernova feedback, and black hole feedback must produce seeds early enough and must feed them steadily enough. They must do this while also matching the number of bright galaxies, their sizes, and their chemical states. The new spectra from Webb act as hard checkpoints. They give line widths, line ratios, and host properties that models must meet all at once. Another piece of the puzzle comes from lensing fields. When a foreground cluster magnifies background galaxies, Webb can reach fainter intrinsic nuclei. This helps count how common early active nuclei are at lower brightness. If they are common, their combined radiation could add to the ionizing budget. Early indications suggest that active nuclei exist but do not dominate at these times. Most of the ionizing photons still seem to come from stars in faint galaxies. Even so, the influence of a single nucleus on its local environment can be strong, and that matters for interpreting the hydrogen signals around it. Black hole spin and radiative efficiency are deeper properties that affect growth. Spin changes how much energy light takes away per unit mass that falls in. Higher efficiency means more light and more push against infall for the same feeding rate. This slows growth for a given brightness. These details are hard to measure at high redshift. For now, studies assume typical values inferred at lower redshift. Even with that uncertainty, the early detections require either heavy seeds or long periods of near-limit feeding. The method used to weigh black holes from broad lines is calibrated at lower distances. It uses the idea that a certain range of line widths and brightness values matches a certain mass based on detailed time-lag studies in nearby active nuclei. Applying this to early times assumes that the structure of the gas around the nucleus is not wildly different. There could be differences. Gas fractions and dust content are lower. Accretion rates may be closer to the limit on average. These differences might change the calibration slightly. Teams express mass estimates with this caveat. Even with it, the masses fall in the millions of solar masses range, which is enough to set strong growth demands. Outflows driven by the nucleus can be measured with line wings and with shifts between different species. Some lines trace denser gas. Some trace more diffuse gas. Speeds of a few hundred to 1,000 kilometers per second are seen in some sources. The momentum and energy in these outflows can move enough gas to matter for the host. Whether this feedback shuts down star formation or just stirs the gas is a source of active work. The early coexistence of star formation and active nuclei suggests that total shutdown is not common at these stages, at least not for long. Linking all these pieces gives a balanced view. Early black holes with millions of solar masses exist. They live in compact blue star-forming galaxies with low metal content. Their spectra show both very fast gas near the center and strong lines from gas across the host. Their growth rates are high, often near the physical limit set by radiation pressure. To reach their masses so soon, seeds must have formed early, and feeding must have kept going with few long interruptions. The exact seed path is still open. The presence of metals points to earlier star formation and supernovae, which could support both stellar remnant seeds and special direct collapse sites in enriched neighborhoods. These results touch the wider story of the first billion years. The energy from growing black holes adds to the ionizing background and shapes local gas. The same spectra that weigh black holes also measure the state of the host. The interplay between star formation, inflow, and outflow shows up in line profiles and in how lines from different elements relate. To place this interplay in context, teams extend observations beyond single targets. They map large areas to gather statistics. They use lenses to reach fainter objects. They add integral field spectroscopy to record motions within galaxies. Rotation and turbulence carry the imprint of how gas moves, how disks form, and how matter reaches the center to feed the black hole. These steps build a common frame for black hole growth and for the assembly of galaxies in the young universe. How do we map the young universe when single deep images are not enough? After the first detections of very distant galaxies and early active nuclei, the next need is coverage across the sky. Small, deep fields reveal the faint population. Wider surveys reveal how common bright systems are, how they cluster, and how environments shape growth. Webb meets this need with programs that tile large areas with near-infrared images, with programs that use the gravity of massive clusters to magnify background sources, and with programs that record the motions of gas inside galaxies through integral field spectroscopy. Each approach adds a piece to the picture and checks the others. Wide mapping begins with a simple idea. Use the near-infrared camera to image large regions with a set of filters chosen to separate distances and types of sources. Cosmos-Webb is one such program. It targets a field that already has rich data from many observatories. The Webb images add depth and sharpness in the infrared. They help find rare objects, such as very bright galaxies at high redshift and galaxies that host growing black holes. They also let teams measure how galaxy properties change with environment, because a large field contains dense regions and more isolated regions. The same filters used in deep fields appear here, so color selections and distance estimates stay consistent. The survey is designed to reach a common depth across the area, which helps build clean statistics. GLASS uses a different lever. It chooses fields that include massive galaxy clusters. The gravity of a cluster bends the light from background galaxies. This effect is called gravitational lensing. It can make a distant galaxy appear brighter and larger, and it can create multiple images of the same background object at different positions. By aiming at these fields, Webb reaches intrinsically fainter sources than it could in blank regions. The price is complexity. The images are stretched and sometimes appear as arcs. To recover the true brightness and size, teams build lens models. A lens model is a map of how mass is distributed in the cluster. It is built from the positions of many lensed images and from the light of the cluster galaxies themselves. With this map, the magnification for each background source can be estimated, along with an uncertainty. Even with this extra step, lensing fields unlock spectra of galaxies that would be far below the usual detection limit. Primer follows another path. It covers two well-studied regions with imaging that matches the Webb instrument capabilities to deep archives from other facilities. The goal is to link Webb measurements with optical data, with X-ray catalogs, with radio maps, and with far-infrared surveys. This link gives a fuller physical picture for each source. It also sets a uniform foundation for follow-up with spectroscopy. When imaging is done with common filters and to common depth, selections are cleaner and biases are easier to measure and correct. Strong lensing clusters like Able 2744 are key nodes in this network. Their mass is high enough to make large magnifications. Webb images of these regions reveal chains of arcs and small compact images that are copies of the same background galaxy. Spectroscopy confirms the distance of each image. The pattern of positions and distances feeds the lens model. Once the lens model is consistent, the team can infer the true brightness, true size, and sometimes the internal structure of the background source. This process turns a complex field into a set of intrinsically faint galaxies with measured properties. Some of the most distant spectroscopic conformations have come through such lensing windows. Integral field spectroscopy adds motion to this map. A standard spectrum gives light as a function of wavelength averaged over some small region. An integral field unit records a spectrum at every point across a small field. The result is a three-dimensional dataset with two spatial axes and one wavelength axis. From this, observers can measure how the wavelength of a line changes from one side of a galaxy to the other. A shift to longer wavelengths on one side and to shorter wavelengths on the other side signals rotation. A pattern with no clear gradient but with broad lines signals turbulence or disturbed motions. Outflows can show up as extra line components that are shifted relative to the main line. These maps use emission from hydrogen and from oxygen to trace the gas. At high redshift, the line from doubly ionized oxygen in the rest optical is often strong and falls in the near-infrared range that Webb can record. At somewhat lower redshift, the hydrogen alpha line moves into the mid-infrared, where Webb's mid-infrared spectrograph can detect it in brighter sources. These motion maps answer practical questions. How quickly do disks settle in the early universe? How common are strong inflows and mergers? How much random motion is present in young systems? How often do outflows carry energy away? The answers vary with mass and environment. In some galaxies, ordered rotation appears early. In others, motions are dominated by dispersion, which is a measure of random speeds. The ratio of rotation speed to dispersion tells whether a system is supported mainly by rotation or by random motion. Simpler language helps here. When rotation is high and random motion is low, gas circles in a calm pattern. When random motion is high, gas moves in many directions at once. Webb finds both kinds. This mix points to different pathways of growth even at early times. Wide surveys and lensing fields connect these internal views to the larger structure. In dense regions, galaxies are closer together. Interactions and minor mergers may be more common. Gas inflows along filaments of the cosmic web may be stronger. These conditions can feed both star formation and black hole growth. In more isolated regions, growth may be steadier and less disturbed. Cosmos Dash. Webb's large area allows counts of neighbors around each galaxy. This simple statistic, often called environment density, correlates with properties such as size, star formation rate, and the presence of an active nucleus. Patterns are already visible. Bright, compact galaxies with strong emission lines appear in both dense and less dense regions, but the fraction with signs of an active nucleus tends to rise in the denser parts. This is a trend, not an absolute rule. It guides models of how gas supply and interactions shape early growth. The balance between area and depth is managed carefully. Wide surveys go shallower than the deepest pencil beam fields, but they cover many times the sky. They catch rare outliers that a small area could miss. They also reduce the impact of field-to-field fluctuations, which happen because the universe has structure. Lensing programs have a small area but reach faint intrinsic luminosities due to magnification. Together, these programs sample the average galaxy and the extremes. The same instruments and calibration pipelines support both, which keeps measurements consistent. Planning these observations is a logistics task. Large mosaics require many pointings with small overlaps. Each pointing uses a sequence of offsets to smooth detector defects and to reach uniform coverage. Background levels and the angle of the observatory to the Sun are kept steady to maintain thermal stability. Spectroscopic masks for multi-object modes must be designed with care to avoid overlap of spectra on the detector. For integral field spectroscopy, exposure times are set to reach enough signal in each small spatial pixel while keeping the total time practical. Lensing fields add an extra step. The lens model is updated as new multiple images are confirmed and the magnification map is refined. This loop improves the estimates of intrinsic properties for all sources in the field. The data volume is large. Catalogs of sources include positions, fluxes in many filters, shape measurements, and simple flags that mark possible issues. Spectroscopic catalogs add redshifts, line strengths, and line widths. Integral field datasets add velocity maps and line ratio maps. Public releases allow many teams to test ideas and to cross-check results. For example, one group may measure the luminosity function in a wide field, while another group measures the same function in a lensing field after correcting for magnification. Agreement across methods makes the result more secure. Differences point to selection effects or to calibration steps that need attention. These surveys also tie into work at other wavelengths. Radio and submillimeter arrays map cold gas and dust. X-ray surveys flag active nuclei at lower redshift and set limits at high redshift. Optical images from earlier missions add shorter wavelengths that help constrain the slope of the ultraviolet light. Far infrared measurements, when present, test for hidden star formation. In regions with strong lensing, the combination of Webb and millimeter facilities can measure both the stars and the gas at high resolution. This builds a more complete picture of the energy balance and the material budget in early galaxies. One practical benefit of wide mapping is the identification of targets for detailed follow-up. A galaxy with a strong line at a redshift where hydrogen alpha falls into the mid-infrared can be observed with the mid-infrared spectrograph to measure star formation directly from that line. A compact source with a suspiciously strong rest ultraviolet line can be targeted for higher resolution to look for a broad component that would mark a central massive object. A diffuse arc behind a cluster can be mapped with an integral field unit to trace how star formation and motion change along its length, which corresponds to different parts of the same background galaxy magnified by the lens. The surveys also test how feedback operates on larger scales. Outflows driven by stars and by active nuclei can be traced by the width and shift of lines in the stacked spectra of many galaxies. Stacking means combining many spectra aligned by redshift to improve the signal of weak features. In wide fields, stacks can be made for subsets split by brightness, by size, by environment, or by the presence of an active nucleus. Differences in line shapes across these stacks reveal how common outflows are and how strong they are in different contexts. Early results show that outflows are present across a range of masses and that their speeds can reach a few hundred kilometers per second. This is enough to move gas out of small regions and to stir the medium in larger ones. Lensing adds another view of feedback. Magnified galaxies sometimes show clumps and filaments resolved at very small physical scales. Spectra across these features can reveal local velocity gradients and shocks. Shocks are sudden changes in speed and pressure seen in gas when fast flows hit slower material. They leave signatures in certain line ratios. Mapping them along an arc shows where young stars drive jets or winds and where gas flows converge. These observations connect the physics seen in the early universe with processes that are also present in nearby star-forming regions, though at different scales and conditions. The same surveys that chart early galaxies also return rich samples at intermediate redshifts. These samples provide a bridge between the first few 100 million years and later stages when disks are common and metal content is higher. By measuring how line ratios, sizes, and motion patterns change with time, teams build a timeline for how gas settles, how feedback evolves, and how the link between star formation and black hole growth shifts. This timeline is an anchor for models that try to follow gas from the intergalactic medium into halos, into galaxies, into stars, and into central engines. Uncertainties are kept in view. Lensing magnification has errors that affect intrinsic brightness and size. Environment measures depend on the completeness of redshifts. Motion maps can be blurred by limited spatial resolution, which makes the rotation gradient look weaker than it is. To reduce these effects, teams compare methods, simulate observations, and propagate uncertainties through their calculations. The tone is patient. Claims are updated as better data and models arrive. This care keeps the broader lessons solid even as details shift. The practical impact of mapping at scale is clear in the current picture of early growth. Counts of bright galaxies at redshifts around 10 to 12 are somewhat higher than older expectations, but not as extreme as first hinted by color selections alone. Faint galaxies are numerous, which supports a strong contribution to ionization. Active nuclei exist early, with masses of several million solar masses and with growth rates that are high. Motion maps show both rotation and turbulence, often in compact hosts. Outflows are common and can carry significant energy. Environments vary, and clustering boosts the growth of ionized regions in dense areas. Lensing confirms that intrinsically faint systems share many of these traits when we can reach them. These large programs also prepare the ground for detailed work on smaller scales. The same integral field methods that unravel motions in distant galaxies can be applied to nearby nebulae to trace shocks and flows. The same mid-infrared sensitivity that catches warm dust in early systems can reveal ices and molecules in cold clouds and disks. The same careful calibration that supports counts in wide fields supports precise time series for planets. The link between the largest structures and the smallest forming systems is made through the common language of spectra, motion, dust, and gas. What does a baby star look like when it first turns on? To answer that, the telescope turns from the far past to our own galactic neighborhood. Nearby clouds of gas and dust are places where stars are forming right now. They are cold, they are dense, and they are filled with structure. Infrared light passes through much of the dust, so the view is clear enough to see details that earlier pictures could not show. With sharp images and precise spectra, it becomes possible to watch how gas falls inward, how young stars push back, and how the basic materials for planets gather and change. In the Carina Nebula and in Orion, images reveal long, narrow streams from newborn stars. These streams are called jets. They are fast and collimated flows that shoot out from the poles of a forming star. Where the jets hit nearby gas, a shock forms. A shock is a sudden jump in temperature, density, and speed. The shock heats molecular hydrogen and other species, and they glow in the infrared. The same regions show cavities and pillars shaped by radiation from massive stars. The mix of jets, shocks, and carved structures tells a story of push and pull. Gravity draws gas in. Young stars and massive neighbors send energy out. Spectra add numbers to these shapes. Emission from warm molecular hydrogen traces shocks and the edges of outflows. Lines from ionized sulfur, iron, and neon appear where radiation is strong. Ratios between these lines yield temperatures and densities. When the telescope uses integral field spectroscopy, each point in a small patch has its own spectrum. From these, motions are measured. A shift to longer wavelength means gas is moving away. A shift to shorter wavelength means gas is moving toward us. The result is a map of speed and direction superimposed on the image. In these maps, knots along a jet have different speeds. The foot of the jet near the star is often the fastest part. The bow shock where the jet meets the cloud glows and slows. This is not a guess. It comes directly from the measured wavelengths. Outflows do more than make pretty shapes. They regulate growth. Gas falling toward a star carries angular momentum, which is a measure of rotation. Outflows and jets can remove part of that angular momentum. They also carry momentum outward. Momentum is mass times speed. When fast gas from a young star slams into the surrounding cloud, it can sweep gas out of small regions. Measurements of flux, density, and speed allow teams to estimate the momentum carried by outflows. In many cases, the momentum is enough to clear gas from the immediate surroundings. This change can slow or stop further infall onto the star. It can also open pathways for radiation to escape, which changes the temperature and chemistry nearby. The telescope measures not just movement, but also the state of the gas. Simple molecules show up in emission when warm. These include hydrogen molecules, carbon monoxide, and water vapor. In softer radiation fields, ices survive on dust grains. In stronger fields, some molecules break apart. The instrument that covers the mid-infrared is especially important for this part of the work. It records broad features from silicate dust, bands from simple organic molecules, and narrow lines from gases at a range of temperatures. In the same region, it is possible to see hot, shocked gas, warm dust near young stars, and cold material deeper in the cloud. Star formation often happens in clusters. Massive stars within a cluster can quickly change their environment. Their radiation carves cavities in the cloud. Their winds push on nearby gas. In the Orion region, for example, the front where radiation meets dense gas is bright in specific infrared bands. By measuring these bands, the pressure and the rate at which the front moves can be inferred. Behind the front, small globules remain. Some host young stars with disks. The survival of a disk near strong radiation is not simple. It depends on the balance between the heating from outside and the density of the disk. Observations show disks that are being eroded on their outer edges while still feeding their central stars through their inner parts. This slow erosion affects how long a disk can nurture growing planets. Protoplanetary disks are the next step in this path. A disk is a flat, rotating structure of gas and dust around a young star. It is where planets form. The telescope detects both the warm gases close to the star and the cold ices farther out. The Ice Age program targeted a cold cloud in Chamaeleon 1. In that cloud, background starlight shines through dense material and picks up absorption features from ices on dust grains. The spectra show clear signatures of water, carbon dioxide, carbon monoxide, ammonia, methane, methanol, and carbonyl sulfide. The temperatures are near 10 Kelvin, which is very cold. At such temperatures, atoms and small molecules stick to grains and react slowly on their surfaces. Over time, they build more complex species. Methanol, for example, forms when carbon monoxide on a grain surface gains hydrogen atoms one by one. These inventories tell us what solid materials will be available when grains grow and when parts of the disk warm enough to release ices back into the gas. Closer to the star, the disk is warm. The near-infrared and mid-infrared spectra reveal water vapor, hydrogen cyanide, acetylene, and other gases. These are found at radii where rocky planets can form. In the system called PDS-70, water vapor appears in the inner disk regions. Carbon dioxide traces gas farther out. The pattern of molecular features with wavelength reveals the temperature and the location of the emitting gas. Inner regions with water vapor point to a rich supply of oxygen-bearing molecules where rocky planets could accrete with access to water. Farther out, carbon dioxide and carbon monoxide dominate parts of the chemistry. This radial structure is not static. It changes as the disk evolves, as grains grow, and as planets begin to clear gaps. A key concept in disk chemistry is the snowline. A snowline is the distance from the star where a given molecule changes from gas to ice on grains. For water, the snowline sits closer to the star because water freezes at a higher temperature. For carbon dioxide and carbon monoxide, the snowlines sit farther out because they freeze at lower temperatures. The location of each snowline depends on the star's brightness and on how much heat comes from gas falling onto the star. Snowlines matter because ice coatings make grains stick more easily. They also change the elemental ratios in the gas that remains inside a snowline. The telescope detects signatures that trace where each snowline lies. It sees water vapor inside the water snowline and water ice absorption outside it. It sees carbon dioxide gas inside its snowline and carbon dioxide ice absorption beyond it. These boundaries guide where giant planets and icy bodies tend to grow. They also set the starting chemistry for any atmospheres that planets later acquire. Disks are not smooth. The telescope resolves spirals, rings, and gaps in some systems. These structures can be made by forming planets, by variations in how the disk accretes, or by magnetic effects. Spectra taken across a disk show how the mix of molecules changes with position. Near a gap, some molecules drop in strength while others rise. This could be due to temperature changes or to dust filtering that blocks radiation in some zones. Over time, grains drift inward and outward. They carry ices and organics with them. When ices cross a snowline and evaporate, the gas chemistry changes. When gas cools and ices form again, molecules lock into solids. Through these cycles, the disk sets the initial conditions for planets and for any early atmospheres around them. Aromatic hydrocarbons also appear in many regions. These are ring-shaped molecules made of carbon and hydrogen. Their collective emission makes broad features in the mid-infrared. They are often called PAHs in technical work. The telescope detects them in photodissociation regions, which are places where far ultraviolet light from stars changes molecules and heats dust. The strength of these features and their ratios vary with the local radiation field and with the size and charge of the molecules. By measuring these changes, the lifetime of such molecules in strong radiation can be estimated. Destruction can be fast where the radiation is intense. Survival is longer in shielded parts of a cloud. These lifetimes affect how much complex carbon material is available to mix into disks and planet atmospheres. Jets from young stars connect the inner disk to the larger cloud. They are launched close to the star, likely from the inner disk or the immediate surroundings where magnetic fields and rotation interact. The telescope sees knots along jets where shocks heat the gas. Line ratios give the shock speed and the fraction of molecular gas that survives. Some shocks are dissociative, meaning they break molecules apart. Others are non-dissociative and heat molecules without breaking them. The type depends on speed and on the magnetic field. This detailed view informs how jets carry away angular momentum and how they stir material on scales of light years. Over time, the energy and momentum from many jets can help clear a region of gas and shut down further star formation nearby. Feedback from massive stars has a wider reach. Their ultraviolet light strips electrons from atoms in large zones. Their winds and eventual supernovae add energy and heavy elements to the cloud. The telescope measures both the ionized gas and the neutral gas near these stars. Ionized gas shows up in lines from hydrogen and from ions such as oxygen and sulfur. Neutral and molecular gas show up in infrared lines and in absorption features from ices and dust. In places where radiation is strongest, aromatic hydrocarbons weaken and dust grains can change in size. In places with more shielding, ices remain and complex organics grow. This variety across small distances shows that environment plays a strong role in setting what materials later feed into disks and planets. The same chemical signatures that appear in nearby regions also appear in distant galaxies, scaled by distance and by time. Early galaxies sometimes show dust even within a few 100 million years after the Big Bang. Long wavelength observatories confirm this dust through cold emission. The telescope adds mid-infrared signs of warm dust and simple molecules in a few luminous systems. The presence of dust so early sets limits on how fast supernovae and massive star winds can produce solids. It also points to grain growth in dense gas, which can proceed when ices coat grains and help them stick. By comparing these early signs with the detailed view of dust and ices in nearby clouds, a link forms between the first solids in the universe and the materials that build planets today. Reliability in these measurements matters. Spectra can be altered by background subtraction errors or by small drifts in detector response. To guard against this, observations repeat with slightly different pointings. Instruments that overlap in wavelength cross-check features. Lines are identified by their exact wavelengths and by appearing together in expected patterns. When a molecule is claimed, teams look for more than one feature from that molecule. They also consider other species that could imitate the same feature. This cautious approach has stopped some early claims and strengthened others. It keeps the inventory of gases and ices on firm footing. Time adds another dimension. Some young stars vary as material falls onto them in bursts. During a burst, the inner disk heats. Water and other molecules change state. Spectra taken at different times show these changes. A feature that was in absorption can shift to emission if a layer warms and begins to glow. These changes inform how quickly chemistry responds to heating. They also show how dynamic the inner few astronomical units of a disk can be during the years when planets begin to assemble. The link from clouds to planets is not only chemical, it is also mechanical. The same outflows that clear gas from cluster cores also set the density and pressure in the regions where disks live. A disk that forms in a very crowded place with strong radiation will evolve differently from a disk in a quieter part of a cloud. Observations test this. In regions with many massive stars, disks can be smaller and may lose outer gas faster. In regions with fewer massive stars, disks can survive longer. Both pathways exist. This diversity feeds into the range of planet systems that later appear. As for planets, the gases we see in disks foreshadow what can appear in atmospheres. Water vapor in the inner disk suggests a path for water to reach rocky worlds. Carbon-bearing molecules in outer regions suggest a path for carbon-rich ices to feed giant planets and comet belts. The ratios of carbon to oxygen in gas and ice can influence the types of molecules that atmospheres hold when they form and evolve. The telescope's instruments measure these ratios in disks. Later, the same wavelength ranges record the signatures of water, carbon dioxide, methane, and other gases when a planet passes in front of its star or when the planet's dayside glow is in view. The bridge from raw material to final atmosphere is made by following the same molecules from cold clouds to warm disks to the air of a world. Through all of this, the tone of the results is measured. Images open windows into hidden regions. Spectra turn shapes into temperatures, densities, and motions. Inventories of ices and gases ground the story of what planets are made from. Shock maps and outflow speeds show how young stars shape their birthplaces. Aromatic hydrocarbons and dust features show how complex carbon material survives and breaks. Snowlines reveal where solids and gases divide. Together, these threads make a clear path from the collapse of a cloud to the start of planetary systems. The next step on this path is natural. Once planets form in these disks, their atmospheres can be read by the same infrared light. The same detectors that measure water and carbon dioxide in a disk can measure them in a planet's thin rim during a transit. The same stability that maps faint jets can hold a steady view of a star while a planet passes. The same care with calibration guards against false signals. With these tools, the ingredients seen in birthplaces connect directly to the gases we find around distant worlds. What can a planet's air tell us about the world below it? The path here is direct. We followed water, carbon dioxide, methane, and ices from cold clouds into warm disks. The same infrared light now reads thin layers of gas around distant planets. When a planet crosses in front of its star, a small fraction of starlight passes through a thin rim of the planet's atmosphere. Gases in that rim absorb light at specific wavelengths. The pattern of small dips across wavelength is a fingerprint of those gases. When a planet moves behind its star, the star briefly blocks the planet's thermal glow. The difference between light with the planet and light without the planet is the planet's own emission. By repeating this across wavelengths, we learn what the air contains and how hot it is at different layers. Webb is steady and cold, and it sees from about 1 micrometer to about 12 micrometers with high precision. So these tiny signals can be recorded and compared across multiple instruments. A first clear case was WASP-96b. It is a hot gas giant that orbits close to its star. Early transit data showed a detailed pattern from water vapor. The water features had shapes that matched expectations from lab measurements and models of light passing through a thin atmosphere. This gave confidence that the instruments, the calibration steps, and the analysis methods worked on the sky. Soon after, WASP-39b became a testbed that used several instruments and modes together. In that atmosphere, carbon dioxide appeared clearly as a broad feature. Even more, a feature from sulfur dioxide was present. Sulfur dioxide forms when light from the star drives chemical reactions that change the mix of gases. This is called photochemistry. The detection showed that light-driven chemistry is active and that the data are precise enough to pick out such products. These spectra also carry signs of clouds and aerosols. Clouds and aerosols are small particles suspended in the air. They can mute some features in transmission by making the atmosphere more opaque at many wavelengths at once. The shapes of the water and carbon dioxide features and the level of the baseline between them give limits on how thick clouds and aerosols can be and at what heights they sit. Data that span from about 1 micrometer to about 5 micrometers help constrain clouds near the deeper layers. Data that reach out to about 10 micrometers help constrain aerosols that affect the mid-infrared. By combining the near-infrared imager and spectrograph with the mid-infrared instrument, The view is continuous enough to separate gases from hazes with better control. Turning spectra into gas amounts needs careful methods. Teams use models that calculate how light passes through a layered atmosphere and how molecules absorb at each wavelength. This is called radiative transfer. They choose a simple set of assumptions for temperature with height, for how gases are mixed, and for cloud behavior. The models include line lists for each molecule. A line list is a catalog of wavelengths and strengths for all the absorption features of a molecule at many temperatures. For water, methane, and carbon dioxide, these line lists have been updated with new lab data and theory. Better line lists reduce errors in where features sit and how deep they should be. Teams then use statistical tools to find which combinations of gas abundances and temperature profiles match the observed spectrum. This process is called retrieval. To guard against hidden biases, independent groups run separate retrieval codes on the same data. Agreement across codes is a key check. One source of confusion does not come from the planet. It comes from the star. Stars have spots that are cooler than the average surface and bright regions that are hotter than average. These features can change the spectrum across time. When a planet crosses a small patch that is different from the rest, the apparent spectrum of the transit can shift slightly. To handle this, teams include simple models of star spots and bright regions in their fits, and they use light curves at multiple wavelengths to separate the effects. In some cases, they also gather emission data or phase curves, which record how the planet's light changes as it orbits to help break remaining ambiguities. Stable pointing and repeat visits help reveal patterns from the star that would otherwise blend with the planet's signal. The same tools are now reaching smaller and cooler worlds with care and patience. K2-18b is a super-Earth or mini-Neptune around a cool star. Webb saw methane and carbon dioxide in its atmosphere. The pattern fits a hydrogen-rich air over a water-rich interior, which is one class of structure for such worlds. A hint of dimethyl sulfide was reported from one analysis. This molecule is of interest on Earth, but the evidence at this time is not secure. The signal is weak and sits near other features. It requires more data and checks with other instruments and repeat visits. This is a case where restraint is needed. A single feature at low strength is not a solid basis for claims. The standard of proof calls for multiple features from the same molecule, repeatability across instruments, and consistency with the rest of the atmospheric state. For very small rocky planets, the task is harder. TRAPPIST-1b and TRAPPIST-1c are close to their cool small star. Emission measurements at thermal wavelengths show that they do not have thick carbon dioxide atmospheres. If such air were present and dense, it would leave a clear signature near about 4 3/10 micrometers and near about 15 micrometers. The absence of those features, combined with the measured dayside brightness, points to little or no thick carbon dioxide. Stellar activity adds noise for this system. Flares and magnetic features can change the star's light on short timescales. Teams use careful baselines and multiple visits to separate these effects from the planet's signal. For now, the conclusion is modest and useful. Thick carbon dioxide does not appear around these two planets. Other gases at lower levels remain possible but are below current sensitivity. Not all atmospheres are probed by transits and eclipses. Webb also uses coronagraphy to directly image some planets. HIP 65426b is a young giant planet far from its star. The mid-infrared instrument resolved it and measured its thermal glow. The spectrum shows a cloudy atmosphere with warm temperatures for a young giant. Because direct imaging isolates the planet's light, it gives a clean measure of the planet's brightness without starlight passing through an atmosphere. It complements transit work by reaching wide orbits and by sampling different ages. Coronagraphy needs very stable pointing and careful calibration because even small leaks of starlight can hide or mimic a faint source. The detection in this case shows that Webb can deliver planetary spectra at mid-infrared wavelengths where clues to clouds and chemistry are strong. As the sample grows, phase curves will become more common. A phase curve is a record of the planet's emission across a full orbit. It shows how heat moves from the day side to the night side. It gives wind speeds and helps map temperature with longitude. For hot planets, phase curves show whether heat is carried efficiently. They also reveal whether clouds form on the night side and survive into the day. These data are demanding because they ask for long, stable stares. They reward the effort by breaking degeneracies that remain in single transits or single eclipses. Combined with spectra, they turn a one-dimensional profile into a two-dimensional map. Every step rests on calibration. Detectors have small quirks. Readout patterns can add faint stripes or steps. Thermal drifts can change the baseline slightly. Pipelines correct these effects using data from dark frames, flats, and repeated observations of standard stars. When teams publish, they include tests that show how robust their results are to choices in the processing. They try alternate baselines. They remove parts of the data to see if the answer changes. They share code and invite others to replicate the analysis. This culture keeps confidence high and helps catch subtle errors early. The standard for life claims is especially strict. A robust case would need several gases that together do not fit known non-biological sources under the measured conditions. It would need measurements across multiple wavelengths and multiple instruments. It would need to repeat across time and across transits. It would need to show that surface pressure and temperature allow a stable climate where those gases can persist. For small rocky planets, current limits are set by stellar noise and by instrument sensitivity. Upper limits are still valuable. They rule out thick atmospheres of certain kinds. They guide models. They help choose targets for longer programs. Nearby cool stars are the current focus because the signals are larger, but their activity makes the task slower. Patience and repeated checks are part of the plan. Even when life is not the question, the physics and chemistry of exoplanet air push models forward. The sulfur dioxide in WASP-39b required photochemistry in a radiation field stronger than Earth's. Retrievals of water, carbon dioxide, and methane across the 1 to 12 micrometer span set pressure levels and temperature gradients. Constraints on clouds test how aerosols form and settle in hot atmospheres. Emission spectra at mid-infrared wavelengths anchor the temperature structure at deeper layers. Together, these pieces force updates in how we treat opacities, vertical mixing, and light-driven chemistry at high temperatures. These atmospheric results also feed back into the broader story of galaxy evolution. They call for better lab data on molecules at temperatures from a few hundred Kelvin to a few thousand Kelvin. They motivate new line lists for methane, carbon dioxide, water, and other gases with more complete coverage. They add demand for lab work on aerosols, including how particles form, grow, and change with radiation. The same lab data help interpret mid-infrared features in disks and in galaxies. As the archive grows, models of how dust and gas cycle from clouds to disks to planets and back into space will be tuned against a common set of measurements. The missions on the horizon are built with this path in mind. The Roman Space Telescope will map wide areas in the near-infrared with stable imaging. It will find rare targets and set uniform baselines for deep follow-up. ESA's aerial mission will survey hundreds of exoplanet atmospheres in a systematic way. It will gather transmission and emission spectra across a common set of bands and build a large sample with uniform methods. Giant ground-based telescopes will bring high spectral detail to bright targets. They will measure wind speeds through tiny shifts in lines and resolve fine structure in emission features. NASA's planned Habitable Worlds Observatory aims at Earth-sized planets around Sun-like stars. It will need exquisite starlight suppression and stability. The standards and lessons from Webb feed directly into the design and into the observing playbooks for these efforts. On the ground, archives and pipelines are being built to last. Data products include raw counts, calibrated spectra, and higher-level maps of gas abundances and temperature profiles. Metadata record the exact settings, temperatures, and backgrounds for each exposure. Crosslinks tie planet observations to disk observations and to lab data. This structure lets teams test new models on old data without redoing all the calibration steps. It also invites independent checks, which are essential when claims are subtle and signals are small. There is a practical rhythm to this field now. Choose targets that match the instrument strengths. Design programs that cover key wavelengths from the near-infrared into the mid-infrared. Include visits that catch both transmission and emission when possible. Repeat to check stability and to average over stellar noise. Use multiple retrieval codes, check sensitivity to priors and to line lists, share results and uncertainties clearly, adjust plans as new lab data and better models arrive. Each part may seem modest by itself. Together, they turn tiny dips and small changes in brightness into solid measures of gases, temperatures, clouds, and winds. The early picture is grounded. Hot gas giants show water, carbon dioxide, and signs of photochemistry. Cloud and aerosol properties can be bounded. Some small warm planets lack thick carbon dioxide atmospheres. A few cooler sub-Neptunes show methane and carbon dioxide in hydrogen-rich air. One directly imaged young giant glows in the mid-infrared with clouds in view. Strong claims about special molecules at very low levels remain open and are being tested with more data. Each result is a point on a map that will grow denser with time. The connection back to formation is already visible. Water vapor in inner disks matches water in close-in atmospheres. Carbon dioxide in outer disks matches the gases seen farther from host stars. Snow lines measured in disks set where solids form and where gases dominate. Those boundaries shape elemental ratios in the atmospheres we now read. The cycle continues as planets evolve and as atmospheres lose gas, gain gas, and change chemistry under light and under outflows. By tracking the same molecules across these stages, a continuous story emerges from cold birthplaces to active skies. All of this rests on the same qualities that shaped the mission from the start. The mirror is large and cold. The instruments cover a wide band and overlap. The pointing is steady for long hours. The background is low and stable. The processing is careful and open. The tone is patient and skeptical in a friendly way. Claims are tied to tests. When differences appear, they become paths to learn rather than reasons to rush. This approach is slow by design. It is how faint signals become firm knowledge about air on worlds we cannot see directly with our eyes. The road ahead is clear and full. Wider samples will map how atmospheres depend on star type, planet size, and distance from the star. Phase curves will chart circulation and cloud patterns. High-resolution spectra from the ground will measure winds and chemistry at fine detail. Lab work will fill gaps in molecular data and aerosol behavior. New missions will take starlight suppression and stability further. Each step will carry forward the same standards that Webb helped set. In that way, the infrared fingerprints recorded today will anchor the search for habitable conditions and, in time, for stronger signs that a small world holds a steady climate with gases that point to processes we do not yet see elsewhere.